Okay, hi everyone. All right, today it is Tally, Bainon, and me, and we are going to be talking about metamathematics, and we might call Jonathan if we have to, but we're going to be exploring, in a sense, the physicalization of metamathematics. And partly, my test is, can I explain to Tally what I'm talking about? That's the start of it. Okay, so the idea is that we think we have a theory of physics. Our theory of physics is computational. The theory of mathematics, the sort of fundamental theory of mathematics, is also computational. It says you take these axioms, you use them to go from either expression to expression or proposition to proposition. You build up this kind of network of proofs and so on. And so in a sense, the raw material of mathematics has been, since Euclid, basically, been in some sense computational. We now think the raw material of physics is computational. What can we learn from this commonality? Because it's a sort of a new fact that the raw material of physics is computational. So kind of the direction this is going is to say, from the things we know about physics, how can we import those into mathematics? In particular, can we make a physicalization of metamathematics, so to speak? Is this making sense so far? Yeah?
To me, yeah.
Okay. So, and the most interesting thing is that this network of theorems idea is basically like our multi-way systems that we think are what are underneath physics and particularly underneath quantum mechanics. And so the question then is, to what extent can we make, aggregate statements about mathematics? So here's a way of thinking about it. So imagine that we know the underlying axioms of mathematics. Let's say we have, in the NKS book, I have this summary of kind of a couple of pages that sort of show the underlying kind of axioms of mathematics in this sort of standard areas of mathematics. So now the question is, if we imagine the infinite future of mathematics, right? So given an axiom system, we can, in principle, grow this multi-way system that contains where paths in that multi-way system where paths of the multi-way system correspond to to proofs in mathematics. I have a question on our live stream from Sam about whether this project is all about extending causal sets. In a sense, yes. That's a complicated story. There's a pretty good Q&A answer on our website about it, but it's a sort of a big extension. Hopefully we'll maybe we'll make some other connections with it here. Okay, so a question then is, so let's imagine that we have some, we can make some typical, let's just go ahead and do this. Something simple here. Let's just make some very simple things so we know what we're talking about. Let's imagine that we have an axiom system, which is essentially just a commutativity axiom that just says AB goes to BA, goes to BA, BA goes to AB. Then we can say, take that, and let's say we have something like this, say 8 steps or something. Let's say states graph. Okay, that's a mess. All right, so let's do this. Let's say graph layout oops, embedding. Okay, so this purports to be a little piece of this very simple version of mathematics, right? So any given, actually, this is a better example than one I've had before, but anyway, so any given, so then a theorem here is, there are various theorems here. Like, for example, a theorem here is the theorem that BA is equal to this thing down here, right? Yes, and so, for example, a proof of that theorem is the, so one proof would be this thing here where we say find shortest path of this, comma, BA to, let's say, that thing at the bottom, BB.
I think the vertices might be a little bit different. You might have to look at them. Multi-way systems sometimes.
I think I just messed this up by just typing the wrong thing. I think this is a much simpler problem for once. Yes, much simpler problem. Okay, so that is a path in this graph, and we could highlight it, and that is a proof, one proof of this fact. There may be many proofs of this fact, right? Make sense?
It does make sense. I don't want to sidetrack you too much, but one question I immediately have, which is maybe too much in the details, is what is the geometry of this particular graph? It's hard to tell because these sort of somewhat redundant pairs of directed edges might be obscuring some symmetry here.
Yeah, there's all kinds of symmetry. I mean, there's just a sorting rule, so there's tons of symmetry in this thing. I mean, in the end, it's a beautiful symmetrical group-like object. But I mean, because the axioms, the implicit axioms of a string multi-way system are associativity axioms, because string concatenation is associative. So what we're adding here, this is essentially an abelian semigroup. By adding this sorting axiom, we're saying it's an abelian semigroup, and what this object is it is something sort of underneath the Cayley graph of the abelian semigroup. Like the Cayley graph would be, let's say we take this for a group, and we can do that in a minute. We can take actual group axioms here where we have inverses and such like. But for this is still a semigroup. And for this, the analog of the Cayley graph will be just to say, what are the connected components? Each connected component is one element in the Cayley graph, right? Because this is, if we do this for a group, okay? So I have some code here. Let's see, multi-way group. Here we go. So let's take this. Let's do this for a group. All right, just so we understand what's going on here. But this is going to, okay. So this is one for a group. So let's say multi-way group. Let's see, what does this have? This has generators, relations, the identity, and inverses. Okay. All right, so if we want to be really swank, we can have our inverses with bars on top and things like that. But let's get a list of generators. So let's say A and B. And let's say, well, the identity element. Well, let's say A and B, and let's say an identity element, let's say lowercase e, and inverses, let's say lowercase a, lowercase b, okay? And let's say relations, let's have no relations here. So this should be the free group, ag. And now we want to start with some initial condition. So I guess what we would do here is what we want to say is we could start from, for example, string tuples. Let's say 5-step states graph. Oh, what went wrong there? That's
I don't think you actually need to give it an initial, do you?
Maybe I don't need an initial thing.
Because the generators should imply that, right?
Yeah, okay, let's try this. Oh my gosh, 83,000.
Yeah.
Okay, let's just try 2 steps here. Okay, all right, there's our free group. Okay, let's take a look at let's go only 1 step. It's pathetic that we only got 1 step. Oh, look at that. Okay, so this is the beginning of the free group, and every one of those disconnected components should be, actually, you know what? Why don't we just take the identity element to be a null string? Is that going to work, or is that going to confuse it? Should work. So now let's say 2 steps here. What a mess. Okay, well, let's see what happens if we just have 1 generator. The free group with 1 generator is going to be a rather unexciting thing. Okay.
Will you explain this to me? Will you, maybe once we've,
well,
I assume I'm serving as a proxy for the audience here, that
well, I'm trying to, okay, so what is this? This is saying, what this is doing is this, I hope this piece of code here is just implementing the relations in a group. So what it's saying is, for example, A inverse is the identity element. Okay.
mm-hmm.
Now, what I admit that I'm a little confused by here is there is so this is saying that there's an element of this multi-way system that's going from the identity element. This is, I see, so this is what's happening is the generators in this multi-way system, the generators are being produced from the identity element by those 2 edges there. Okay, so
Yes.
there's another identity here. So this.
So around, can I make some guesses and you tell me if they're right?
Yeah, this is an attempt to generate words in yeah, go ahead.
The different kinds of edges that are showing up here, the different ways of getting edges. So one will be to take any of the generators and apply it on the left or on the right to the particular vertex.
Mm-hmm.
And we can see that happening if you just look at the empty box in the middle. Oh, well, on the left and the right, they're the same thing. So generator A going off to the left, and also the inverse going off to the right. But you can see that applying the generator to the left and to the right does yield 2 different things at the top and the bottom, where we've got little a, big A, and big A, little a on the top and on the bottom. So that's one kind of edge, is just applying a generator on the left or on the right. And then there's another kind of edge, which is applying a relation. We don't have any relations here. And then there's another kind of edge, which is applying an inverse on the left and on the right, I assume.
Yes, which is essentially a relation, an implicit kind of relation.
Do we have to have any inverses? So if we left off little a,
well, then it isn't a group.
Well, it would be a semigroup, I guess, right?
Yeah. If it's a semigroup, then we'll have an analogous version of this picture. I mean, if we take the analogous thing here, let's say, I think I have code for semigroups as well. But before we go too deep into this, I want to zoom out a little bit to understand what the point is. And then we'll go back into this, because I really want to go through this in more detail, because this is going to be relevant, I think, to what we're trying to do. All right, so here we've got generators. We've got I don't think we have inverses here. And we don't have an identity. Okay, so in this setup, what this is doing is, I'm not sure this is the way I would have done this, actually. I need to remind myself what I wrote years ago in the NKS book about this very topic. Let me just look here. Always a good source for to know at least what I at one time understood. Okay, so a lot of what we're talking about here is actually what I discuss, and I should actually bother to read what I wrote before. Always a good idea. After 25 years, one tends to forget. I mean, this is kind of the analog of one of those proofs, but this is in the context not of strings, but of tree-like systems, right? Right. So that's a tree-like proof, right, where you've got an XOR type operation in it. It's the same idea. It's not and let me see. What's this? So maybe I should read that. Oh wow. Okay. That's always good. Huh. That's a note I should actually read. I mean, this is talking about the correspondence to systems in which, yeah, right. So that's a string, and if we want to, let me just make a note of where that is. So what is this? I see. This is giving the explicit rules that are needed to make a string-based substitution system, right? This is just the correspondence to one of these systems with operators in it. This is just saying that the thing is that strings are have implicitly added an associativity. That's not a remarkable fact. What I was looking for here was the correspondence to group theory. Let's see. Oh boy. Okay, I should read this stuff again. So this is about using lemmas, which will be important later. I mean, let me try to sketch the overall picture. I'm just looking for. Boy, I understood this decently well 25 years ago. Now I just have to recover what I understood or thought I understood.
The systems that you're looking at there in the book, these operator systems, are they? Do you think they're the same as the multi-word group system, or what's the idea?
No, not quite. The operator system, the point of the operator system is to have just a general expression, a tree-like expression with let's say a binary operator or an n-ary operator, okay? And that n-ary operator, you can call it dot or something. And what you're saying is you're defining the axioms, define transformations between trees, just like in Wolfram language patterns, right? And a difference between that and the hypergraphs of our physics models is that the hypergraphs are, in a sense, just two-level things. That is, the hypergraph is just a collection of relations between elements, whereas the tree structure allows you to have an arbitrary depth, but where what's happening is, but you are also maintaining order, right? So in other words, you have a tree, and the tree is a binary tree, but you're maintaining the ordering of the tree. Make sense?
Right. It has to be rooted. So it's like with the hypergraphs, there can be completely symmetric situation, like a cycle. There would be no way of representing that as a tree, because you'd have to chop it at some point to flatten it into a tree.
So it's just a slightly different kind of thing that you're transforming, but I don't think it makes a huge difference to that. I'm now curious what on earth I wrote in this. I'm just, I really need to read what I wrote before. This is terrible. But what I'm looking for right now is the relationship between two groups. Let's see. Oh, come on. Okay. What I'm looking for is the where I talk about the correspondence between oh boy. So this is about quantifiers and whether I don't think this is relevant. We shouldn't get too wound up in this, but I think we do need to understand this to understand that way of generating this multi-way. Where do I have?
Let me ask the obvious question, Stephen, would be if we think of a multi-way system in which the rules are literally mathematical rules, mathematical rewrite rules.
Yep.
Rule delayeds. And
yep.
the initial condition is an expression. It's extremely well defined what that is. That will be a multi-way system in general. Have we studied those?
Not adequately. I mean, that is, that's the story of arbitrary evaluation chains, right? So, the evaluator does one traverse through that multi-way graph. The evaluator is effectively doing, I mean, in a sense, the evaluator is doing a single proof. I mean, this is, I think the fancy version of the Curry-Howard correspondence or whatever else, that this whole business about, proofs of programs type thing. That's really saying the evaluator takes a single traverse through this graph.
Yeah.
Right. And the question of what an arbitrary, I mean, so, simplifying it to say take only one operator, let's say one binary operator, no, that has not been adequately studied. And that is I just started studying these things as essentially multi-way generalizations, as what I was calling symbolic systems, which are kind of also analogous to combinators, right? Because
the combinators are a special case of those. They just happen to be Turing, some of them are Turing complete instances of mathematical rewriting.
Right, exactly. But you can study the general case of that. You can study the ones that aren't complete. But I think the big story of the multi-way graph is still the same. And a lot of what I was going to talk about today is really just about a story. Well, it starts with a story of multi-way graphs. Then the multi-way graphs have to be interpreted for mathematics or for physics. And that's where these kinds of issues are going to come in. But I'm still a little frustrated that I'm not finding my my whole discussion. It's really upsetting to me how many things I actually did understand 25 years ago that I've completely forgotten. This is one that Jonathan rediscussed recently, and I had completely forgotten that but what I'm looking for is the discussion of how this relates to things like Cayley graphs. Oh, let me just do a search here. Here we go. This is the discussion. Okay, always good to actually take a look at this. So, right. Semigroups. Okay, so what we have in a multi-way system is a semi group, right? So in a semi group, one has so what we're saying that okay.
Aren't they called magmas or monoids or something like that?
Which?
When you relax the requirement of inverses.
No, I think this so-called semi-TUI systems, I don't think they have a name in the traditional, I don't think. I mean, monoids are just having an identity element. I don't think they have a name other than semi-TUI system or production system. Okay. So let's just look at, I mean, here I talk about, okay, given a particular representation of a group in terms of rules for a multi-way system, often used as the Cayley graph. Okay. So I think the Cayley graph is sort of a complementary thing to what we're getting in this representation here, because what it's saying is you are identifying everything. I mean, you know, I had a version of this that was another piece of code I wrote where you're just applying the group relations. You're not applying this additional weird thing that is generating elements, right? You're just applying group relations. So that means that given a particular, so we could do that. We could write something which just applies group relations. So for example, we might say AA goes to nothing. Well, yeah, AA goes to nothing. AA goes to nothing. I think I had a resource function that actually did this. Those two relations, then we want to say, what else do we want? We want nothing goes to AA, nothing goes to AA, and that should be the free semigroup on one element. Those are the relations for the free semigroup on one element. So if we say multi-way graph of that, what we should get, I mean, it's not very exciting, but what we should get is, if we now say, for example, resource function string tuples, and then let's say we say AA, I don't know, 3, for example. Let's say 3 comma states graph. Oh gosh, 2 comma states graph. Okay, so these are the separate elements, right? These are the things which in the Cayley graph are all just turned into a single element, right? Single node in the Cayley graph. Make sense?
Okay.
You understand what's going on here, yeah? I mean, this is here. Let's take a simpler case. Let's take this case here, right? So these are each elements where, right? These are all things that are just related by the relations in the group. These are all words in the group related by the relations in the group, right?
Mm-hmm.
I mean, and unless I got something wrong here, oh, I see. Oh, this was kind of crazy of me, right? So this particular walking through the group is going to be particularly sort of extreme because I'm allowing identity going to AA, for example, and that's causing me to go, you know, that's generating lots of identities here. Make sense?
Yeah. If you wanted to only append, because I mean, the typical generator thing is you can pre-apply or post-apply the generators, right? You don't put them in the middle of the word, which maybe you can do with like end of string arrow A, beginning of string arrow A. I mean, those are string patterns.
Yeah, they are string patterns. I mean, you're just suggesting that we should avoid inserting identity elements in the middle of the string.
Because I guess the fundamental point would be that there's some vertices of that graph that you produce that are actually identical to other vertices under the group axioms, but you haven't given them enough time to settle out. So
sure. Right, but the whole point is that the whole point is every one of these consists of words that are equivalent under the group. Right, every connected component is words that are equivalent according to the group.
Okay, yeah, these are all the same group element actually, which is the identity.
That one is all the same group element. It's all identity, and I'm just trying to explain the relationship between this and a Cayley graph, right? Mm-hmm. The Cayley graph is, because that's going to be important to what we talk about in a minute. I mean, the Cayley graph, it's sort of complementary to the view that we're taking. The view that we're taking for this multi-way graph is, given an element, we can think of the multi-way system as being the reductions of that element, right?
Mm-hmm.
And we can also try and have something where we're also injecting things into the system by adding, I mean, this is the most natural thing to do. It's just given an initial string, we are just generating words that are equivalent to that initial string under the rules of some particular group, for example. Make sense?
Yep.
Okay, so let's go back to the big picture of what we're trying to do. So big picture is we've got these kind of proof structures, right? Okay, so let's talk about what a few facts about mathematics are. So one fact about mathematics is there's no upper bound necessarily on the length of the path you need to get from one string to another. That's basically a statement of the undecidability of the word problem. In the case of a group, that's a statement of the existence of undecidable propositions in, that's the existence of undecidability in J-random mathematical axiom system, right? So that's that story. Now the question is, what I'm trying to understand is if we, so one of the mysteries of mathematics is that the typical questions you ask don't involve those arbitrarily long proofs. That is, that mathematics is sort of doable. So let's give an analogy, right? In physics, it could be the case that everything you care about requires going down to the most microscopic level and looking at every update you want to look at, right? That's the story of computational reducibility, that it could be the case that everything that to know what happens after 1 second in the history of the universe, you have to do 10 to the 1,000 updates because you have to follow every individual update to know what's going to happen. That's the sort of story of computational irreducibility. But in fact, the big surprise of the physics project is that you don't need to go down to that level of detail, because floating on top of that level of detail are things like general relativity and quantum mechanics, which are generic facts that come out from looking at the generic features of this system, independent of all its microscopic details. Does that make sense?
Mm-hmm.
Okay, so the challenge of the day is, what is the analog for mathematics or metamathematics of the bulk statements that general relativity and quantum mechanics make about the physicalized version of these multi-way graphs?
Mm-hmm. If any. I mean, it'd be really cool if there are some, but...
Well, I think that there are. That's why I'm doing this discussion, right? I think there can't fail to be some, because I think that the raw material is the same as the raw material of physics. So in a sense, so let's do another analogy. So another point is, in the physical world, we can imagine the whole history of the universe is just some giant multi-way graph, right? The universe as it was in the past, the universe as it is now, the universe as it will be into the infinite future, it just generates this whole multi-way graph. But in our experience of the universe, we only get to sample pieces of this multi-way graph, right?
Yeah.
So similarly, in mathematics, we can say the ultimate Platonic mathematics is just this whole giant multi-way graph, right? But we, in the human mathematics that we've done, we've sampled only a piece of that multi-way graph. Make sense? Mm-hmm. Okay, so the question is, just like in physics, we can say, we sampled only the stuff around, the Earth or something, but yet there may be laws that apply to everything. We can say the same thing about mathematics. That is, we've sampled a few million theorems of mathematics, but maybe there are general principles about what happens that apply across sort of all mathematics, not just the part we've sampled. So the question is, what might there be?
I'm struggling to understand something, which is the fact that we can prove sort of general abstract things. Like you prove things about graphs, right, or groups, and it doesn't matter what the group is. How does that fit into this picture of little bubbles of computational reducibility in what would otherwise be the hopeless tangle of physics, right? Of microscopic physics.
Right. So I think the answer is that a particular group, and this is where I wanted to do a bunch of specific examples, a particular group is a model of the general axioms of group theory. Right? So this particular thing here, well, this particular picture is the general axioms of abelian semigroup theory. Right? This tells you about things that are true. This set of connections, like the theorems we can prove here, are general theorems true about all abelian semigroups. Right? Okay.
Yes.
So if we have a particular abelian semigroup, there are two ways we can describe a particular abelian semigroup. We can either say we're going to add a bunch more relations to fill in the relations for the abelian semigroup, or we can say we actually have a multiplication table for the abelian semigroup. And I suppose these are equivalent things, but we can imagine, and this is where, we can imagine essentially we can imagine sort of defining a model that corresponds to that particular abelian semigroup. And the claim from previous discussions that we had is that we can think of a model as being like making foliations in this picture. Okay? Because a model basically is saying we are, in a model, one of these strings might have a value, a coordinate position, that's equal to another one of these strings, because the actual multiplication table is some particular thing, right? And so what we're saying is that in a model, we're making foliations here, and in the model, to know whether some two things are equal, we are just going to have to ask, well, and this is where I need to tighten this up a bit. But we're basically asking, in this case, we're asking, in the underlying rules for the system, what follows from what? Okay? And in other words, does this down here follow from this thing up here? Then we'll say, for example, that they're equal, right? Mm-hmm. But another way we can know that this follows from this is to say we've got some kind of foliation of this thing in which this is in a later time, this is a following thing from this. So in other words, this set of relations here defines some kind of partial order. We can try to make we can, for example, make foliations that okay, so there's the claim is that there's sort of a trade-off. There's either you can say, to find whether this is derived from this, you can either go find the collection of arrows, or we can say we've pre-made some kind of model in which we know that these things occur in slices, and then we just have to look at which slice this is in. That make sense?
Maybe need a more concrete example, I guess.
Okay, well, let's try and do a more concrete example.
I'm still, because foliations are pretty non-trivial, right? I'm still trying to think about what foliations tell you when the edges have this particular meaning of, application of axioms of some algebraic system.
Well, so one possibility will be, let's do an example where the foliations are just a count, where we coordinatize this by counting the number of A's and B's.
Okay.
That may not work very well. I mean, what we want to do.
Well, hold on. So in that particular example, all of these are equal because the rules don't change the number. So
yeah, they're all equal. So, which is not a very interesting case.
No, but if we had more rules, so if we introduced generators, so if we introduced A's and B's on the left and on the right, we would be changing the things. So the point would be that if you have a set of different rules, it could well be that there's some coordinatization that counts effectively how many times you applied one of a family of rules. So these two rules don't change the A-B counts, but the generators that introduce new A's and B's would change the A-B counts, right?
Sure.
So then it becomes a non-trivial coordinate scheme. I mean, it's actually useful.
But then I don't think that's any more a model for standard. What's happening here is this multi-way system is sort of modeling the standard operation of axiom systems. Whereas as soon as we're introducing new generators, I don't think we've got quite the same scheme going on.
Well, we don't have any generators at the moment. We're just stuck with the number of A's and B's that you started with in the word.
That's correct. That's correct. But
Yeah.
that's what you do in, when you prove that something is equal to something in a mathematical system, in universal algebra, for example, you're not saying, oh, and let's introduce a new thing, because then you get something which isn't equal. I mean,
True.
you can, right? So I think the thing we have to think about here is, okay, so one thing we can clearly do here is we can add to this some completion, so to speak, which says, let's jump ahead in this picture, right? So for example, here, if we take this thing and let's add a, let's add a lemma. Okay, so we've got this, and now let's add, let's see, this thing here, A, B, B, triple A, B. Okay, so now we'll add that lemma. Okay, so now certain proofs that we had before will have gotten shorter.
Mm-hmm.
Okay, so the question is, how do we think about,
well, surely you've introduced some homotopy into this picture, right?
yes.
Because now you can have, or homology, because you can have a hole, you can have a path that takes you the long way around and then the short way around via that shortcut that you introduced, and you can't shrink that path anymore.
Why not? You can, in this case. You can shrink the path, because this thing is just a speed up. It's not changing where you can get to. But instead, what this is doing is, it's thinking about it in terms of this foliation idea, it's looking at it in a different frame, because what we're doing here, let's imagine that we have a, am I making sense? So if I remove that.
It's very hard. You happen to have chosen a complicated enough system that I have no visual intuition.
There's no crutch here. Let's make it simpler. Let's make it simpler. Okay?
Make 1B. Use an initial word that has exactly 1B in it, because then that'll introduce quite a lot of symmetry.
Okay. Well, first of all, let's just look. We've got multiple complicated things going on here, which are unnecessary. Okay. So let's just say we have ABB. Well, okay, ABA.
Okay.
Okay. That's probably too trivial. So let's say AABA. Let's say. Okay, there we go. That's one of decent complexity, I think. Okay, so this now
is it complete? If you make it go for 20, would it be any different?
No, that's complete.
Okay. Okay.
All right. So now, okay. So this is saying, okay. So in a sense, we are in one particular frame right now, where we can say this. Let's imagine that we aggregate the one. What's special about each layer here? How do we characterize the layers here?
If I can rephrase that, how do we coordinatize?
Yes.
To bring out some kind of symmetries or some kind of structure.
Right. Well, one coordination is just to say the time value of this thing is the number of updates you have to do from here to get to that thing.
Mm-hmm.
Right? Okay, so let's say we add another rule here, which is consistent with those rules. So let's say we add the rule, I don't know, AAB goes to ABA. Okay, which is clearly consistent with the rules that we have. Okay, so now, boring. Why didn't that do anything?
I think you should go with 1B, because it's incredibly regular, and then you can make more A's. So the regularity will become really clear.
No, but
that means that yeah.
Okay.
Just can you try? You can,
okay.
Go back to this, but so harmless.
Okay, what are you suggesting?
Lots of A's and one B. Just put a B at the end. I like that because now I can understand the system.
All right, okay. Okay, so then let's add to that system something which is another rule, right?
Mm-hmm.
So for example, AAB goes to ABA.
Well, the obvious one, Stephen, is that the one with the B at the end goes to the one with the B at the front, because you're just closing the loop.
Okay. Okay, there we go. So AAB goes to BAA. Okay, so now we've got a comparison between those two things. And what's happened is we've traded off the intrinsic rules in the underlying system with having more complicated rules here. And that's allowed us to shortcut the process of going from AAB to B. I didn't even get, oh, I see. In this one, it's, yeah, that particular thing is a two-step process there, right?
Yeah, it seems more symmetrical to have done AAAB to BAAA, the full length case, 4 A's.
Okay, I didn't do that.
Just because those are the two ends of the. Yep.
Yeah, I mean, so that's just showing there's a direct path there as opposed to going around the big long path.
We've pre-computed this particular axiom, this particular lemma.
Right.
Yeah.
Okay, fine.
Okay.
So look, the thing I'm trying to get to is, is there an understanding of some analog of reference frames in this metamathematical space by using models? That's step one. And then try to understand what's the analog of causal graphs here. And then the goal is to understand essentially the goal is to try and derive something, first of all, relativistic results, and second of all, kind of general relativistic results from this. Okay. That makes sense? Because the claim is that there is a certain sense in which, the underlying physics here is independent of, if models are thought of as foliations, then the statement that, that the graph is the same underneath is some statement of model independence of certain results.
Can you explain the claim about models being thought of as foliations?
Yeah, well, let's go through that claim. I mean, that claim is still a little bit vague, right? The claim is, okay, what is a model? A model, let's go through some explicit examples of what we mean by models, right? So a model, example of a model, a particular group versus groups, groups in general, right?
Yeah.
Okay. So how do we get a particular group? Well, there are two ways we could do that. One way we could do that is we could add one approach, add relations to the generic axioms to force us to have a particular group, right? Make sense?
Yeah.
Okay, another approach would be to say, we have a representation, right? And in that representation, another approach is an explicit multiplication table. i.e. representation. Make sense?
Mm-hmm.
Okay, so let's do an example here of what we mean by that, right? So when we have an explicit multiplication table, that means that one of these words, I think I'm losing you here, but I mean, one of these words is, you know, the word is some kind of, you know, we can just compute for every pair, we can compute what the result was from the multiplication table. Yes?
Yes. Yep. But
Okay,
I'm just thinking, like, computationally, you know, one way, as you said, one way to have a model is, you know, here's a program, and the behavior of the program implements the behavior of the group, right? It represents elements of the output of the program correspond to group elements. Applying the program twice is how I multiply, you know, that kind of mapping. It's like
I'm not sure that quite works, because what we're saying is, look, in this case, an explicit multiplication table here, you know, there are a set of inequivalent words on which this all operates. Am I making sense? If we're going to represent it in terms of words like this, that's what we have to do. We have to, we could as well represent it in terms of group elements, right?
Mm-hmm. But you could also use, for example, like matrices as being the representations of the group. And that's totally, it's totally legitimate way to do it. So what's the general pattern behind these models of the abstract?
So what I'm saying is that what you can do is, this here is writing out, I think, you know, we're writing out words, we're writing out elements of the group. We have a word represented by a sequence of generators, right?
Mm-hmm.
Here. Okay. So some of those words are identical by the relations of the group, right?
Mm-hmm.
Without any group relations, none of these words are identical.
Yep, the free group.
Right. Well, it's, yes. I mean, yes, or a free semigroup or whatever, right? I mean, in general, with strings, it will be a free semigroup. Make sense?
Mm-hmm.
I'm just noting the inverse square law of tallies, that you're now further away from your camera, so you're much more, you subtend a much smaller solid angle, which makes it hard to tell what
inscrutable.
Yeah, right. It's
always felt, anyway. I might just be riffing here, but it's always felt like groups are really about action. They're about time, right? They're about like doing a sequence of things and the result being the same as if you did a different sequence of things. That's where the relations would come in, right? Like a structure of a particular group tells you how actions compose.
Yes.
Because fundamentally time is there. Like the words that you're building represent a sequence of actions of some kind. I mean, that's, well, just one way of thinking about groups, but it's how I like to think about them. And of course, inverses correspond to undoing something or going back in time.
Right. Well, but I mean, so one sense is, in a group, you can be, you know, adding, you know, what one notion of group, one notion of time in a group, which isn't the notion of time in metamathematics, by the way, involves basically appending generators one at a time. That's kind of, does that make sense? I mean, I'm going to explore this group. I'm going to find out what's here by adding generators to words.
I mean, that's the very definition of a generator, is the generators are the things that allow you to access any element of the group by just doing that. Indeed. That's what makes them generators, right? So yes, I agree.
Right. You know, i.e., this is a way to construct an object that corresponds to the group, right? In other words, if what we do is, I think that's what that multi-way group thing is doing, that's saying that we can construct an object that is and in the case of the free group, that object, I think we had some pictures up here of what that looks like in the case of the free group. Do we have that? Yes, this was the one element free group, so to speak. Right?
Yeah. Yeah,
And
these are sequences of actions that you can reach after doing 1, 2, 3, etc. things at a time.
right. But one of those actions is, so there are two kinds of actions. One is the add a generator action, and the other is the apply a relation action. Right?
I suppose that's not really an action. That's just...
Well, it depends how you think about it, right? Depends how you think about it. In this picture of the multi-way system, it is much more granular than what you normally think of in a group. I mean, in a group, as soon as you made a generator, this is how you make a Cayley graph, is you just say, apply these generators, and then everything, all of this stuff here is squashed to a point. Everything, all of those edges aren't there. It's all just modded out.
Yeah, exactly. And so that's why it's important, I think, for these things to emphasize that the edges are of different types. I mean, they're not colored, but they could be to illustrate that some of those edges are the application of generators, and other edges are the application of one of the relations. And if you mod out by one color of that thing, you'll get the Cayley graph, right? If you mod out by the relations, you'll get the Cayley graph.
Some edges correspond to appending a generator. Others to applying a relation. I agree. Right? Okay. All right. So let's go back to, I just want to paint the big picture here, and we'll try and go to the smaller pieces. Okay. So, I mean, the big picture is trying to understand, I'm trying to understand metamathematics in bulk, if that makes sense. Right? Because normally in mathematics, you are understanding, every theorem is a unique thing, so to speak. The goal of metamathematics, or this kind of continuum metamathematics, is to understand mathematics in bulk. Just like we understand space-time in bulk. That is, we could take the point of view that, this particular place in space has a name, it's called Bob or something, and that's what we want to concentrate on. But we don't do that. We think of space in bulk, right?
Well, maybe some of the dictionary is already clear to you. So, for example, the role of geodesics, like they're shortest proofs. Okay.
Yep.
In this picture,
what's that?
Proper time along a geodesic is measuring step by step how long the proof takes you to do. Is that roughly right?
That's right. And the idea is that you can make a change of frame by the claim is, and that's this claim about models, is that there are two alternative ways to figure out whether something is okay. So this is an interesting claim, that there are two ways to figure out whether something is true in mathematics, so to speak. One is to symbolically follow the proof, and the other is to say, I know what thing that is in terms of a model, and to conclude something just from the model, from a fact about the model. Okay, so the concept would be, and let's again go back to the question of groups, right? And a model of the abstract concept of a group is a particular group, right? Which might be finite, it might not be finite, whatever. It's any group obtained by adding relations to the free group is going to be, in a sense, a model you can think of as some kind of model of the free group. Model of groups in general. We're having various people on our live stream are pointing out all sorts of things, like a group can have multiple Cayley graphs depending on the generators you select.
Yeah,
yes,
totally.
Sure.
But if I can rephrase what you've just said, because I think I get it, and maybe if I say it in a slightly different way, you'll agree, and then I'll know we have the same idea. it would be that there are some truths that are evident from, that are going to be true of any group, and so will be true of a particular group. And you could demonstrate them by doing calculations in that particular group, or by just saying, oh, but that's an axiom of group. I mean, that's a general theorem of group theory that we know for all groups, and therefore it's true of this group, of this particular model, right? That might not even, you might not even think of that thing as a group. It might just be the integers or whatever.
Yes.
And then there are going to be particular truths that are only true of the detailed structure that arises from some particular group, some particular model. And there's no theorem of group theory that comes from that. It's just an accident that it's true for one particular thing.
Right.
But for a particular truth, you could get access to it those two different ways in some cases.
That's correct. That's correct. You could say something, you could prove some general result of group theory by instantiating it in a particular model of group theory that corresponds to that particular group.
Mm-hmm.
Right? Okay, so the claim is going to be that when looked at in bulk, okay, this is the attempted claim. When looked at in bulk, this notion of models is like the notion of reference frames, aka foliations in these multi-way graphs.
Can you say that again? I'm sorry.
Okay, so the claim is that the notion of models, and again, this is what I want to tighten up. The notion of models is related to what we have previously thought of in the space-time case as the notion of reference frames.
Okay.
Okay, so what is a reference frame? A reference frame is a way of making an equivalence class of, we could say, I mean, if this was in space-time, which it isn't, but we can consider the space-time case. I'm just thinking to what extent we can view this. Okay, let's ignore that. Okay, what we're effectively doing is we're saying we're making an equivalence class of states here. Think of these as states, these nodes, right?
Yes.
An equivalence class of nodes that corresponds to the things that we will consider to be, quote, simultaneous, if we were thinking about this in space-time. Make sense?
Okay. Mm-hmm.
So, and normally, when we invent simultaneity, it is a convenient way to make sense of space-time. That is, we could just say, for every point in space and time, these are things which follow from that point. But it is convenient for us to say, no, if it happened now somewhere, then, and it happened that I don't think I'm explaining this as well as I would like to be able to be. But the whole point is that making foliations is a way to make sense of space-time, is a reduced description of space-time in which we're not having to say every point has its own separate history. We're able to say this slice of space-time has can have an effect on this subsequent slice of space-time.
Well, can I suggest tightening the phrase making foliations to coordinatizing, right? Because that's a bit stronger than making foliations. They just introduce a time coordinate. That's not the only kind of coordinate you could have multiple coordinates. And maybe a good analogy that would help me is with the project that me and Antonia did on evolution, in which you can say that the mutation graph or the species graph, I guess, can produce every possible biological organism. Of course, almost all of them would die or would never be born in the first place. And you can capture that fact just via foliation. You say that those things do occur, but at infinite time, right? So foliation can represent natural selection. It can represent a preference for certain things to occur and others not to occur, or relative frequencies. Even though in theory, everything is treed out at some point. And maybe there's a similar thing here, right?
Yeah,
maybe
let's understand that. You're saying, okay, so let's understand what you said there. So you're saying the mutation graph of the DNA mutation graph contains everything.
Mm-hmm.
But
it's the Library of Babel, right? It's in the Borges story.
yeah,
Every
right.
book is present. It's not interesting and it contains no information.
Right. But then what you're saying is the fitness landscape of the world, you say, causes you to say that that particular mutation you want to foliate as occurring only at infinite time. So it's like there's nothing new under the sun, but like the trilobite occurred early, but something else could have occurred early by mutation, but didn't. I mean, is that basically your statement? I mean, that
sort of, yeah.
I mean, it would say that the humans could have occurred 1 billion years ago, in principle, by virtue of, but I think it's the case that, see, one of the things that tends to happen, and one of the things that's interesting, is these light cones that you get, which relate sort of progression in time with relationship in some version of space. And that's, I think, where really non-trivial things start to happen. Right? And so the question is, what's the analog of the light cone in that evolutionary case?
Well, I mean, it's a funny thing, I suppose. I mean, and in the context of metamathematics, it might be that the analog of natural selection or of a fitness landscape is some sort of human preference for aesthetic qualities of the particular theorems, right? Or particular theorems. I don't see what the choice is, really.
Sure.
Like
That's right. I mean, ultimately, platonically, all of mathematics already exists, like this Library of Babel. Right? But we are merely, just like in the physical universe, we're merely exploring certain parts of, we have lived through a certain time. And, we're also exploring, well, I mean, it's a little different because I mean, we could pick it would get really kind of weird if we said, we just don't care what happened in this part of the universe. We'd increasingly get incompatibility by saying that part of the universe hasn't evolved. And that's where the light cones come in. We can't maintain that consistently for very long. We could say, but okay, let's. By the way, somebody is asking how the monster group fits into this. I just for fun, I can point that out. I mean, it is simply a set of relations. I mean, we could write it down. There's the icosahedral group, and I don't know how many relations the monster group has. It isn't very many. And what that's saying is that what one is saying is that if we were to enumerate all possible, the statement that the monster group is a finite group is the statement that if we look at all possible sequences, given a particular way of setting up generators, if we looked at all possible sequences of generators, all possible words, there are only a finite number of equivalence classes of those under the reductions corresponding to those relations. In other words, that now I don't know what the statement that something is a finite group, if we allow this possibility of appending group elements here, what does it mean that something is a finite group? It means that when we append group elements, we'll always get thrown back into the thing that has, what does it mean? Appending the group elements doesn't really get you to anywhere new because it's a finite group. And so the number of inequivalent, unreachable, you're no longer looking at new territory, so to speak.
Mm-hmm. But I mean, the multi-way system would still be infinite, right?
That is correct. Yeah, I think that's correct. And because you're adding longer and longer words, you're injecting more and more generators to add longer and longer words, but those words will always have paths back to somewhere else. So it's not like you could imagine that there's a prong where you never get back. There's a one-way prong, so to speak, but that could not happen.
How would you control that?
Well,
I mean, it feels like a bit of a weakness of this way of thinking about this, is it sort of like veers off into these infinite.
No, that's only in the case where, I think it's Jonathan's code that makes what he was calling a multi-way group, where it's simply, willy-nilly adding generators. Okay? In this way of doing it, where all you're doing is to look at the relations, that doesn't happen. You're just saying, when are two words the same? Answer, there's a theorem that says they're the same when there is a path that goes, from one word to the other word, right? So just to understand, I mean, by the way, the sort of, there are homotopies here that correspond to the equivalent proofs. There's a homotopy between different proofs of the same theorem, right?
Can we understand that a bit more?
Yes.
I mean, I find that it's the thing that I first left to too, and I just kind of much beyond what you just said in my head.
Well, okay. So I mean, all we're saying is there's a way of, there can be two different paths that two different paths that prove the same theorem, right? In the sense that they have the same starting point and ending point. Now,
and a lot of those paths will be only superficially different, right? They'll differ by a small little delta that's explained by one of the group axioms.
Sure, we can always we can deform one path into the other by adding completions, aka group axioms. Any path can get deformed to another path by just adding more relations that simply map the elements from one path to the elements of the other path.
Okay. But if I have total freedom to add those axioms, then I can just make any path the same as any other path. So there must be some, I don't understand, when are two paths fundamentally different? Like, what are the obstructions to the trivial homotopy?
Well, I think what a lot of what is discussed in, homotopy type theory and things like this has to do with the actual transformations that go from one path to an equivalent path.
In a picture like this, is it obvious what those trivial things are?
Yeah, those things are yes, it is obvious. In the theorem proving approach, it's saying you're adding completions. A completion says there is a branch, you start from one node and it has a branch pair that can go in two different directions, right? If you want to conflate those two directions, you need a completion which says the two elements of the two things that come out in that branch pair are taken to be equivalent. In other words, you add a relation that conflates those two elements in the branch pair.
Okay.
Okay. So that's what it means. That's how we implement, sort of going from one path to the other. And that's why, in the homotopy theory, okay, so in the category theory interpretation, right? Just to go over that. I mean, these would be isomorphisms in the category theory interpretation. If they're just one-way arrows, they'd be like morphisms. So in the category theory interpretation of this, we have to understand, category theory is to, what's the right analogy? I mean, the physics project is sort of expression rewriting with expressions that don't mean anything, right? Where all of the, where all the actual identities of the heads have been removed, so to speak. Does that make sense? And so similarly, it's, I mean, what we're talking about here in bulk metamathematics is category theory, well, and in the physics project in general, is category theory where the objects in the categories mean nothing. Right? Where it's purely the superstructure of category theory. It's purely, we have, we have these objects and we have morphisms and so on, and the morphisms are just arrows, and all we're looking at is the structure of those arrows and so on, right?
Kind of like what Wittgenstein did to philosophy, but to mathematics. I mean, word games is not that far off from.
Well, yes, it's that's the meta in matamathematics. Is what we're doing is okay. So in any case, let's go back to this. So the question here is, if we have we have this thing. I mean, we can talk about the category theory interpretation if we want to. I mean, we can say something about that. I mean, the whole point is that just the graph level of this, we can think of as being like a one category. At least if we have transitivity, yes?
Is a one category a category, the ordinary category?
Yeah, it's an ordinary category, right? So the only difference here is that in a full one category, you have, I mean, I don't know what the best example of these things is, that they're horribly complicated, most of the examples of category theory. There's got to be a really elementary example involving just, integers and integers mod something or other, something like that. I need to find what the very most elementary, maybe somebody on our live stream knows this, the very, very most elementary, not requiring any advanced math version of something with
well, a nice one is a nice one.
Yeah.
A nice categories with. Just be more. Sorry, I didn't want to interrupt.
Go ahead.
What kind of categories?
No, I mean with a bunch of morphisms.
Yeah. Well, linear algebra is a nice one. So
that's already kind of complicated. But go ahead. Tell me about that.
Objects are vector spaces of whatever dimension.
Yeah.
And morphisms are linear maps between those vector spaces. And what's nice about that is that, like, obviously composition works, right? If you have something from Rn to Rm, and something from Rm to Rp, obviously you can compose them and you'll get a linear map from Rn to Rp.
Sure.
And then you have things like the initial object would be, I guess, the empty vector space, the zero vector space. I don't know if there's a final object. There's probably not a final object. And products, I'm sure, are things like tensor products in the obvious way.
Yeah, you can certainly do that, but that, you don't need that for ordinary category theory. You're just looking at, this sequence of morphisms.
Yeah.
And what we're saying here is that the analogous thing in our multi-way system, there's a fine sequence of morphisms that allows one to think of this thing like as being like a one category. And as we start thinking about these transformations between proofs effectively, those are like two categories.
Okay. Why is it a one category? Because I don't see how morphisms compose in that picture we had before.
It's a weak one category. It's a weak
what does that mean?
Category. It means it doesn't have the transitivity property.
Oh, okay.
I mean, it's just a name. I mean, yes, no, I mean, you need to add transitivity, which it does not have. I mean, the thing that, Jonathan has been excited about and Xerxes have been excited about is this thing that the limit of when you take both, mapping from proofs to proofs and the mapping of mappings of proofs to proofs and so on, when you take the limit of all those things, you get this Rullial multi-way graph that I started looking at. Remember the one for Turing machines? And so the claim is that that Rullial multi-way graph is an infinity groupoid. You're not supposed to
Okay.
laugh about that.
No, I'm sure it's very cool. It's just
Let me explain why.
Yeah, sure, go ahead.
Okay, so the whole point is that what's happening is to make a mapping from proof to proof, you're adding certain completions, right? You're adding certain additional rules. Okay? That's how you're making that mapping.
Okay.
Okay? So imagine that you add all possible rules. You just say any rule that's conceivable, any rule that you could write down is applicable. That's what the rulal multiway system is.
Yeah.
Right? But that is also something where those all possible rules will be the things that get you from proof to proof, from proof of proof to proof of proof, and so on.
Okay.
Right? So inevitably, sort of almost by definition, the rulal multiway graph is the infinity groupoid.
What is an infinity groupoid?
So it's the thing that you get by taking a category, okay, and you take this, you make, and then you're making, you know, a 2 category up to an n category by taking, instead of just morphisms, you take the mappings, you know, these functors from one category to the other. You're going, and then you take
so maybe you can just help me understand a 2 category. So category objects and morphisms, I'm happy. Yes. I know what functors are. They're the things so that the diagram commutes.
Yes.
But do you now use those as now being objects in some higher thing?
Yes. Those then become, right. And then you're using those themselves. So in our case, that will be the thing that would take this proof here into this proof here. So that's effectively mapping from morphism to morphism.
It's mapping from morphism to morphism. Okay, that's mapping from that whole chain of morphisms.
Yeah, in this particular case, to that one.
Down to one morphism. Okay.
Right. And so the idea is that the thing you get by doing that, I mean, I'm no expert on this stuff. I mean, but I believe is what's considered to be the 2 category. And then as you keep going, you're generating an n category where you just keep doing that mapping. You keep taking the, you know, these sequences and mapping, these morphisms and mapping them to other ones. You keep doing that. And eventually, when you've done that an infinite number of times, you will get this infinity groupoid, which is kind of unsurprising because the infinity groupoid, okay, why is it a groupoid? It's a groupoid because once you've got all possible rules, you also have every rule and its inverse. And so everything which might have been a one-way morphism now becomes an isomorphism. Make sense?
I didn't follow that last part. So just
okay. So every
groupoid versus yeah.
Right. So a groupoid is simply something that you get by having a instead of just morphisms, you have, I think you have, every morphism is a 2-way thing. So an isomorphism. Okay. And also it has an identity element. Each object in the groupoid has an identity morphism, which corresponds to an arrow going back to the thing itself, right?
That's true of ordinary categories, but I suppose with a groupoid, you also have that every morphism can be composed with another, its inverse, such that you yield the identity for that object. That's then a groupoid.
No, because the thing is going from one object to a, you know, there's a mapping from one object to another object and from that object back again.
Okay, and then I guess it has to be both ways round.
Yeah. Right. So and the point of a groupoid, I guess, is that in an ordinary group, if you think about an ordinary group categorically, it's only one object. and it just has a bunch of morphisms that map back to that object.
Yeah.
Right? Whereas a groupoid, there are many objects, and you have these morphisms that map between objects.
Yeah. Exactly. Okay.
Okay.
So this infinity groupoid captures all. This is weird. I'm just trying to wrap my head
All
around
morphisms
this.
between morphisms, and so on.
Okay.
And so the point here, the big deal.
Does the infinity category contain all the other smaller categories as subcategories, as objects within it, or something?
It contains them as some kind of fibrations, I think.
Oh God. Oh, okay.
And okay, so I mean, why does one care? One cares because of this growth and decay hypothesis that says that once you have an infinity groupoid, then it necessarily has certain topological or perhaps geometric properties. That's the claim. And that, in a sense, this infinity groupoid is like a renormalization group fixed point in physics, where by going sort of, and by the way, okay, what is the analog of mathematics? In metamathematics, the infinity groupoid is the mathematics of all possible axiom systems. Right, so you can imagine enumerating possible axiom systems. Each axiom system corresponds to like a field of mathematics. In this infinity groupoid, you're just throwing in all axiom systems, right? So that you have all transformations corresponding to any set of axioms. And then to get any particular field of mathematics, it's some kind of fiber inside this infinity groupoid. Because what you get by following only those paths that correspond to a particular set of axioms that were a subset of the infinite set of axioms that you put into the infinity groupoid.
Yeah, I get that part. And that's why I think coordinatization of even these simpler multi-way groups could be quite interesting to look at. So
no, I know, and that's what we should look at.
Especially if the coordinates correspond to which particular subsets of the rules, those edges come from.
Yeah, right. So we want to look at coordinates, but I'm trying to set out the kind of the big picture here,
because you know what? Then like non-trivial, like powerful lemmas or any kind of theorem really would represent unexpected relationships between coordinates, right? They'd be like, you do this 3 times, you do that 4 times, and you wouldn't expect it, but it's the same as doing this other thing once, right? It's like a little bit of torsion in the geometry of applying
curvature,
these different...
I think, not torsion,
curvature. Well, can't you see them as just aspects of the same thing?
Which? Well, torsion
portion.
tends to be, that's asymmetric metric tensors and stuff like that. That's different from saying that. I mean, what you're talking about is the failure of parallel transport, right? Which is curvature.
I actually mean going north 1 kilometer, east 1 kilometer south, and then west, and then you're not back where you started, which is torsion, but that can also be a consequence of curvature. I think for like discrete things, it's a little bit fuzzy what the difference is, but I'm not the expert.
Fair point.
Obviously.
You're probably right, actually. You're probably right that those two things merge into each other in the discrete case. But in any case, I mean, so the idea would be that you're right, that the presence of shortcuts is, in a sense, if everything was just a grid, and to get from one expression to another, there was just one minimal path.
Yeah.
That's one thing. But the fact that that isn't the case is a reflection. I mean, that's a reflection of essentially curvature in metamathematical space. Right.
That's what I'm kind of getting at. Yeah. Well, another way of putting it is that if things were really boring, you could just keep track of how many times you've applied this axiom, that axiom, and you would have a coordinatization of theorem space. And everything would be very dull because like there would be no way you could fully describe how to get anywhere else.
Right. Nobody would be proud of their mathematics because they wouldn't ever get you just be plodding through it. Nobody would have found a powerful theorem, so to speak.
Yeah.
But right. I mean, so So in a sense, I mean, okay, so one way to think about it is there's a sort of inexorable progress of mathematics, which is what you get by just following every step here, right? I mean, what's weird, okay, what is mathematics? What do people actually do in mathematics? What they actually do in mathematics is they prove theorems, which basically say you can now add to this picture an additional relation, which then transforms this picture by, you know, completing, as you can think of it as a completion. It will conflate two things here. It will crush this picture down. Every time you add a lemma, that's effectively what you're doing. Make sense?
Mm-hmm.
So in some sense then, so what is our picture? I mean, the history of mathematics we could think of as being, I mean, from that point of view, and I'm trying to understand what you know.
I feel like the thing that would bring it down to earth because I think there are different styles of how to think about this kind of thing, and mine is quite. I do enjoy the abstraction, but I also like to see it proved out with really simple examples.
Yes,
because for me, examples are they're the grist that like makes my mental machinery run. These examples, finite examples, and.
Yes. No, we
like
need some examples. We're going to get some examples. Don't worry, we're going to get examples. I'm trying to make sure we understand what direction we're going in, because the thing that, you know, the thing that I think we have been discussing previously is this idea that somehow the presence of lemmas is really a story of curvature in metamathematical space.
It's presumably also a question. It's also a story of what human beings have found. Like, why would humans choose certain things to be lemmas? Anything could be a lemma, right?
Well, there's an intrinsic
true thing.
No, but given a particular field of mathematics, like arithmetic or something, there are lemmas that correspond to paths in this, you know, in the system that were squashed up to, you know, to length 1, right? Now you can say, well, which lemmas do humans choose to put in there? That's a different question, and that's a question of, I mean, that's, you know, the planets continue to orbit whether spacecraft reach them or not. And, you know, I think it's an interesting question, what the effect, you know, there is an abstract metamathematics out there, an abstract mathematics as well, that exists independent of whether humans reach pieces of it.
Yeah.
But what you're saying is that you're saying that we are distorting that what we humans choose to do. See, I claim that's going to be like this foliation story, that we can represent the things that we humans choose to do by the foliations which we use to understand this abstract space that is the inexorable course of mathematics.
And then you would make certain predictions. So one prediction you would make is that the lemmas or theorems that are chosen to be particularly beautiful are the ones that kind of function like an Albacira drive or whatever it's called. Ones that like induce lots of curvature that's useful for taking shortcuts in theorem space, right?
Well, you know,
that capture a lot of curvature.
You know, I had made this list of let's see. Let's see. I'm just
yeah, I'm sure you said something similar to this.
No, but I had an interesting thing, because I had a list of types of theorems that people give, and oh gosh, what the heck would I have called this? This is terrible. I'm so. Oh, that's an interesting one. Forcing of operators by axiom systems. Yeah, that's this question of whether you can use axioms, under what circumstances this is this question of, given a set of axioms, are they about a particular thing? Or do they admit multiple models still? So for example, if you do Boolean algebra, you can make certain constraints, and eventually it will be that the only multiplication table consistent with those constraints is NAND or NOR. In other words, previously, okay, anyway, that's a different thing. But I'm looking at, oh, drat, what on earth?
Well, that's almost the inverse, right? Because if you, yeah, I don't know.
I'm looking for the place where I discuss. I have this kind of list of what counts as a powerful theorem, what counts as what those things mean. It's empirical metamathematics, basically.
Yeah.
Oh, I wonder whether I've got that listed in empirical. Look at that. That's a good sign. Ah, terrific. Look at this. Okay, so these are claims about what. I don't know if these are correct, but a difficult theorem, a theorem having a long proof. Okay, so these are interesting claims. An elegant theorem, a theorem whose statement is short and somewhat unique. I don't know whether that's correct.
Theorem that cannot be readily deduced from earlier theorems, but is well connected.
I don't know if that's right either. I mean, these were just speculations about what the kind of essentially graph theoretical significance of these things these impressions we have in mathematics.
Well, you had this nice idea of like a wavefront of proof complexity, right? And if you terminate it early, you'll see theorems of certain sizes. And yes, you might have to wait a really long time, and then you get a really short theorem out, but it took a long time to get there. That would count as an elegant theorem, I guess.
You think so? Or a difficult? Well, I see. An elegant theorem is one way it took a long time, but it ended up being short.
Maybe. Relative to its proof length, right?
Or perhaps that's a powerful theorem. I'm not sure.
Maybe that's a powerful theorem, yeah. We need a toy domain that is rich enough that there will be a lot of these things in practice that will pop out. We'll be able to like draw some networks of theorems.
I think group theory is the most promising. I mean, I think that the two theorem networks that we have Euclid, we have the theorem network of Euclid, which is less exciting than you might think. Oops, let me just.
Why? That's surprising. I thought it would be pretty cool.
I'll show it to you. Hold on, just.
Oh, it's on this page.
It's somewhere in this book. Yeah,
I mean, no, it's on that page. Stephen, scroll down.
There it is. Okay, simple enough. Okay, so that's the theorem network of Euclid, and we have this in the function in the data repository, so we can actually play with this thing. And actually, because we now have actual capability to do proofs of this type in Wolfram language, we can see everything about these. And I think we have a. Let me just find this for a second. Let's see, mathematics. Oh boy, these are in alphabetical order. What do you know? Okay, this is another version of that. The theorem network from Euclid's elements. That is a really pathetic looking object. What is that? I mean, so what we need to do, let's just put this in here. Okay, so here it is. Okay, so let's see, that is the theorem network. So now let's at least make a layered graph plot of this. Come on, what's it doing? Why is that taking so long? There must be something complicated about this. Oh, there we go. Okay. What do you conclude from this? I mean, I know that the proof that takes, well, let's find out what the proof that takes the longest to arise is the proof of that there are 5 Platonic solids. So one thing we can ask is, there's a question here, what are the 2 clusters? That is a good question. I wonder whether those correspond to different books. Let's see, we could label the books of Euclid by colors here. We could also, I mean, maybe we could just look at a particular book. Okay, so those are the common notions and postulates. Let's see, my favorite common notion, I think, is common notion 1, which is the statement that space is continuous, I believe. Unless that's a postulate, I believe that's a common notion. But those should be the things without degree. It better be the case. Let's find out. Let's select from the vertex list of Euclid vertex out degree. Sorry, vertex in degree of 0. Now, this is going to be embarrassing. If this is, so the vertex in degree of 0 better be, what the heck? What am I getting wrong here? How could there be theorems whose in degree is 0? And why are the common notions not of in degree 0?
Are you sure that the edges point in the way you think and not the opposite way?
That's a good question. All right, let's find that out. Let's look at the out degree. Ah, you were absolutely right. Well, that's encouraging. Okay, that's kind of silly, and we should add that to the documentation for that Euclid. Okay, so there we've got the common notions. So let's find out. Actually, now I'm curious how much of Euclid depends on common notion 1, which is my favorite non-favorite common notion. So we could find out what the light cone basically of common notion 1 is in Euclid.
Yeah, graph highlight of whatever it is, out component, blah, blah, blah.
Right. Okay, so let's say, well, let's do this. In the original Euclid there, a highlight graph of the original Euclid, which is rather big, comma, and then what do I want to say? I just want to say subgraph of Euclid, comma, out, vertex out component of Euclid, comma, and then that common notion. Is that going to be everything, do you think? Oh, look, no. Let's do this just for fun. Let's take Euclid's 5th postulate, and let's see what depends on Euclid's 5th postulate. Did I get this wrong? Is it vertex in component? Is this backwards?
Yeah, it's vertex in component. You're right. Also, you don't need subgraph because highlight graph accepts a list of vertices.
No, I know it does, but I want to make it look nicer by having everything. Okay, so those are the things. That's actually pretty interesting. So those are the things that depend on the 5th postulate.
Do a table of them. 1, 2, 3, 4, 5.
You mean just the vertex in components? So
No, the highlight graph. Why not just show?
Oh, the different postulates.
Yeah.
Well, that's kind of weird.
Oh, yeah, that is odd.
Oh,
okay, this is actually
Jose here is maybe these are the arithmetic and the geometry of Euclid. Maybe this is geometry. Maybe this is all geometry. But the postulates have, let's do the common notions. Let's do the same thing for the common notions. How many common notions are there? I should know that. 5. Okay.
But by the way, what's fun about what we're doing here is that, to go back to
well, so they're different things. So these different common notions. So the first common notion about points seems to affect those pieces. Yeah, every postulate we could color differently, but they're going to overlap a lot.
Stephen,
yeah.
This is a really fun example for a fun opportunity to think about coordinatization, because if we think about distance from the ith common notion, we have a 5 vector, which is, I mean, it's good to think about time, but these are 5 parallel notions of time. And it would just be fun to think about what that tells us.
Yes, right. So, okay, so one possibility, one coordinatization is distance from different common notions. And what you're saying here in general, I mean, there is a geodesic distance in general, but let's go back to this for coordinatizing this thing, right? In this case, there is a geodesic distance from, we could pick 2 points here, basically. And we can coordinatize by just saying there's a vector that corresponds to the geodesic distance from those 2 points. Right?
Say that again?
Given 2 points here, or given 1 point, doesn't matter. I mean, okay, so look, this picture that we have here is a coordinatization by just asking how far do we have to go? What is the geodesic distance from that point to any one of these points?
Yeah, that's exactly, yeah.
Right? So if we wanted to, we could position this, we could pick 2 points here, and we could find where everything is on the plane based on coordinates from the geodesic distances from 2 points.
Okay.
Right? So, and we could actually do that. Let's just do it. I mean, we could say, for this, let's pick one of these slightly more civilized ones. Let's pick this one here, okay? Okay, so now let's say that what we're going to do here is, okay, so here's our thing, and we're going to say, let's pick, so geodesic distance is graph distance from, so let's call this graph GGG or something, right? So we'll say graph distance for everything. We're going to get 2 things. We're going to say graph distance in GGG from, let's say, AA, BBA to element E or something. Well, actually, we just say this. Let's say this. This is what we're going to do. So for
get all the graph distances, right?
Yeah, I want graph distance for every point. Yes.
Yeah.
I want graph distance to every point. And I want
no. Drop the third argument. You don't need that. It already gives you a list of distances if you just only have 2 arguments. So that'll give you a list of the one coordinate, and then you'll have the list of the other one.
Oh, okay.
And then
you just
Stephen, use those as the X and Y coordinates for graph layout.
Exactly.
Vertex coordinates.
I know. I was on top of it. I was on top of that. That was
okay.
Okay. So let's use this one down here. BAAB. AAB. There. Okay. So now what we have, now we're going to take those 2 and we're going to transpose those, and those will become the let's just take the transpose of those things.
Please make this into a function. You so often in these lab experiments you avoid making things to functions until the very end.
Right. Okay. What do you want to do? You want to say graph coordinatize.
Graph coordinatize, exactly. Takes the graph, takes the 2 vertices.
No, it takes n vertices.
Sure, but we're going to want to put them in vertex coordinates.
I know they
Although
are.
that could be
We're
a
going to do
separate
two of
function.
them for now. Let's take n vertices, and this, and what we're going to do then is that will give us a mapping. And what I want to return here is a mapping from vertex list to those sets of coordinates, okay? So this is going to be basically this thing is going to be this, hold on. So it's graph distance in G over that, mapped over vertices, that thing transpose, and then that thing threaded into vertex list of G.
Well, the other way would be to directly set an option on the graph using the option vertex coordinates, right?
No,
if you know it's two.
I'm going to do that. That's exactly what I'm going to do. That's what I'm going to say is graph coordinatize this graph GGG with vertices AA, BBA, BA, AA, B. Oh, for goodness sake, what did I do wrong?
A list.
Okay, there we go. So now my claim is that all I have to do is to say graph of GGG, comma, vertex coordinates, arrow this.
Mm-hmm.
There we go. Okay, so what happened here? So we've got several points that were not distinguished. This is actually kind of interesting. We've got several points here that were in an equivalence class that had the exact same coordinate positions.
Yeah.
Right? So to avoid that, we're going to do a total, absolute, disgusting hack, which is we're going to add a random, we're going to put here random real, like minus 0.1 to 0.1, to plus hash, map that over graph coordinatize of this. This is a total hack, but it should work. What did I get wrong here? Graph coordinatize that. No, what did I get wrong?
I'm going to write a function that does this properly as well while you do
that. What do you mean by properly? I mean, this is, oh, this is horrifying.
So you can use group by to just, all the ones that are in the same equivalence class, they just get collapsed.
Yeah, but that's not going to help us. I mean, that will give us, oh, I see.
Well, then you Y offset them. So the ones that are in the same class, you just add a small 0.1 offset range.
Okay, fine. Let's do it. Let's do it. Let's do it. Let's do it. Okay. So this is so. But the main point is, okay. I just want to think through what we're going to get here. So what we're going to get. This is a coordinatization by virtue of distance from given vertices, which is one form of coordinatization. How general is that form of coordinatization? I mean, because what I'm thinking about is in what I was thinking.
There's a dual thing, just briefly. The other obvious one is the number of times you apply a given relation, right?
Yes.
And similarly, the number of times you apply a given generator, if you want to go all the way back to that picture. Yeah, so it'll be interesting to connect them, but whatever, for now.
Okay, but fine. But I mean, the whole point of coordinatization, let's just review for a second. Models, more traditional notions of models, like we're just going to, a model is a group, is a particular group. That particular group can be identified in these two ways. One is by making a particular multiplication table. The other is by adding relations to produce that, right?
Mm-hmm.
Okay, so this is not about adding relations. This is closer to filling in the coordinate, filling in the multiplication table, I think. I mean,
I don't know if do you want to think of it like that? I mean, I just like the idea that there's a very general way we can imagine any group, any algebraic rewrite system by using a bunch of anchors. And
I agree. I
this
think
kind
that's
of,
good, but I want to understand how that corresponds to what one normally thinks of in mathematics. This is a weird thing. It's word distance, right? It's distance between words, which is not, I think, a very common type of thing. I mean, there is a, but so, you know, because what I want to get to is thinking about these equivalence classes that we are getting by, I mean, here we got a coordinatization that is completely different from our previous one. Our previous one, let's do the coordinatization. Let's just do kind of silly coordinatization, okay? Let's have two identical copies of the same thing. Okay, so now what this is going to do, oh, I see. There, those are just, well, I'm a little confused by that, but basically what this is going to do,
if you use 0 and 1 instead of A and B, it will actually be pretty clear. Well, it'll be clearer because at least we'll be able to see, I don't know.
yes, we might be able to see that. Yeah, right. If we use 0 and 1, then this will be some kind of Hamming distance. I mean, it's probably already some kind of edit distance or something.
Yeah.
In this particular case, because this is just the rewrite, I mean, this is just reordering. It's just going to be a count of the number of, well, the whole thing is just, are you about to write a version of this that is like a, well, here, let's write the proper version. Okay, so you say, what we want to say here is,
so let me feed you the right computational primitives. So it's not actually group by, I think it's position index. So here's the first point to make, is that you don't actually need the vertices. So vertex coordinates can just accept a list in the same order as the vertex list. Okay. That will help. It'll help us a little bit. Then the next function you want to use is position index, because what that will do is it'll find all the duplicates and give you a list of where they occur. So if you just give them a list of coordinates, so 0, 0, 1, 1, 2, 1, 1, 1 again, for example.
Well, here, let's just take this set of coordinates here. Let's take one of these. I mean, so you say that the vertex list is irrelevant anyway. So
yeah, just the transpose for now.
Okay.
And if you do position index, it'll give you access to
the whole thing, just that.
Yeah, just do that. So that's telling you each key is a coordinate.
I didn't remember this function. When did we put this function in?
I actually proposed this function way back when. It would be more useful with a second argument, which I'm annoyed that I never suggested. But anyway. So the values here tell you which indices that coordinate occurred in, right? So what we can then do is with key value map, you can get access. #1 will give you the key, #2 will give you the value, and then we'll just take the key and we'll repeat it several times, but with a little y offset each time.
Yeah. Okay. Fine. Okay. So you're proposing, but then key value map, but it's got to do some kind of folding thing because it's got to remember how many times it's seen that particular key. I don't think that's necessarily the right way to do it. I mean, I think another way to do it will be to say here, to just take this. Look, actually, let me suggest a different possibility. Okay. So let's take this here, and then let's say here, group by last
comma first. Yeah. Or last, because you want to drop, you don't need to remember the coordinates in the second thing.
No, just remember
or
the
whatever.
key.
Yeah.
Well, no, but this thing here, right? You only need to remember so this is effectively values. Isn't that gather by?
It's just gather. Gather will be fine, or gather by last or whatever. But yeah, I see your point. It's just fiddly. I think no, everything will be fiddly.
Yeah, here, let's just do it. Why didn't that get what I thought it would get? Oh, this graph coordinatize. Okay, what's going on here? Are there no duplicates here? Yes, there is a duplicate.
No, gather by did what you want. Look, it put A, B, A, B, and A, B, A, B, A in the same place. Yes, so that's great.
Yep. Okay, so now gather by does that. So now what we want to do is for the gathered ones, we want to, for those that are gathered, we want to take each gathered thing, and we want to do
say all.
Yeah.
Oh yeah, map indexed. Yeah.
We want to say map indexed. What do you want to do? Change the y coordinate? Yeah, let's change the y coordinates.
Yeah.
And that's map indexed of something at level.
It might even be level 3.
We could do level 3, but I was thinking of doing level 2 because it's a bit weird to do level 3. At level 2, we want to say it is, oh God, we need another inner map inside here.
Just make a function. I mean, because then you can use pattern matching and it's so much clearer what it's doing.
Fair enough. Okay. All right, fine. So let's take this gather by.
I mean, that map index was good, but I'm saying apply a function that's net.
I know. So what we want to say is to each of these, we want to say, well, let's just call it munge for now. We want to say munge of each one of these will be of the form.
Well, it'll be key arrow x comma y comma.
Yeah, all right, okay.
And then the index, right, from the map indexed.
Yep. And that wants to go to key arrow x comma y plus 0.05. Minus,
perfect.
Minus 0.05i.
The I has to be in a list on the left hand side. On the the pattern.
Yes. Why not? Oh, that's not going to work anyway because it's got to be the second level map indexed. It'll be the second level.
Oh, so then blank comma. Okay, yeah.
Oh, we just do it this way. Okay, so now what we want to say is here, we want to say map indexed of munge, comma, munge of, okay, I have to do this, last of hash 2, comma 2, if I'm not mistaken.
Nice.
Okay, now we just flatten that. And that's our thing. So now let's do, let's call this, okay, so then this here, let's call that graph coordinatized 0. I don't think this one is going to be a winner here. Let's say graph coordinatize. I know I'm not good about these naming things, but graph coordinatize X or something for extended. See, it's like product naming when people, it's 1980s style product naming.
I was about to say 1980s style programming.
Okay, so now we want to take this, and this becomes graph coordinate as 0.
And GGG becomes G.
And that becomes verts.
And you should do one more thing once all of this is working, is make a function that embeds it into the vertex coordinates as well in one go, because we're going to want to play with this for a bunch of different cases.
Yeah, right. Okay, so let's do this. So graph coordinate is x. So let's just check this. You know what? I want to collect this code. Let's just have a little section here called code and more. And our code is the brilliantly named Munge. That thing is 1970s style programming. Coordinate 0. Coordinate x. Okay. So here we want to say coordinate x of this. Well, looks reasonably convincing. Actually, we probably want to put in here a delta dy with default value, let's say 0.1 something. And that means
you have to pass that dy through to, or just multiply that last by dy, and then drop the 0.5 from I. Yeah. And then, can I suggest two more functions? They're super obvious. So there's graph coordinatized 2D, which just takes graph coordinatized x and attaches graph, vertex coordinates, whatever. And that takes, it obviously takes two vertices.
Yep.
If you want to bother with that, and then the 3D one as well, because why not?
Okay, so let's say verts colon blank comma blank, and then we might as well have a dy just for good measure here. Okay, so this is graph coordinate x of the verts. This is graph of g comma graph coordinate is x of g verts dy. But that is that's vertex coordinates arrow that, right?
Mm-hmm.
Okay. Okay, so now you suggest we make the 3D version of this. All right, let's try running these. Okay, so what we want to do here is we want to say, where is GGG? GGG is this thing here. Actually, we don't care about the layered graph embedding. Well, we might do, but let's just do this here. Okay, GGG is this. Okay, so now we want to say graph coordinatize 2D of GGG, comma, that.
The natural thing to pick would be, you can pick that. It's pretty random. Oh, that's nice. Need more offset, maybe.
Yeah. Well, here, let's just see what that looks like for. Okay, so let's say. Okay.
Interesting. So I'm going to make a prediction, which is if you pick the natural anchor points, which is the two B's on the left and the two B's on the right, things will make more sense. But you might also have to choose an initial condition that makes more sense as well. Yeah.
Okay. So that successfully kind of foliated this thing. What is that doing now? What that's effectively doing.
I think make the offset bigger, Stephen. Otherwise, it's really hard to tell if those guys interact or not. Do they interact?
I don't know.
The problem is that these bidirectional edges really don't add anything, and they just make it harder to see what's going on.
Well, we can. How do we get rid of the bidirectional edges? We can just do. We can do some kind of simple graph thing on this.
Yeah, simple graph.
And then, is that enough? No. What do we want to do?
Undirected graph. It's called undirected graph.
Yeah, I understand. But then we also want to do a simple graph of the undirected graph, because that will take the double edges and turn them into a single edge.
Yeah.
Okay.
So there is actually interaction between them.
Yes, there is.
That's interesting. Well, I mean, this is so much fun now. I mean, we entered very experimental terrain. Like the obvious thing is just crank up the number of A's or B's.
Right. Okay, but so let's just understand what we're doing here. What we're doing here is we are forming a foliation of some kind, a coordinatization that we could have done by taking our original picture and drawing all kinds of coordinate grid lines on it. Right? That's equivalent to what we're doing here. This is a coordinatization of that. Okay, so let's take...
and more than that, it's a continuous coordinatization in the sense that neighboring vertices, distance one vertices, become distance one under this coordinatization. So it's whatever the discretization of continuousness is, the natural one. I mean, it is a natural one, isn't it?
Well, of the underlying multi-way graph, right?
Yeah.
It's
not quite an isometry, but it's something like that. Lipschitz continuous or something like that.
Right, but so what we're thinking about here is, let's think. This is well, okay, what are you suggesting? You're suggesting we should do some bigger cases. We should definitely do some bigger cases.
Well, yeah, there's something very natural is going to happen here, which is the because the rules that you've got just move B's around, right?
Yep.
So you can have one B or two B's or three B's.
Oh, so let's just do AAAB like this. That's totally boring.
Yeah.
And however we coordinatize that, let's just try, let me just try to understand. Let's try 20 steps here, and let's just try lots and lots of A's here. Okay, so that's a one-dimensional object, right? As soon as we have two B's, we'll have a two-dimensional object. So let's take this object here, and let's coordinatize that.
And in general, you're going to start with the initial condition will be one of the coordinates, and the string reverse of the initial condition will be the other coordinate.
Okay, so that's just doing the obvious thing, right? Okay, so now the claim would be, if we take the initial condition to be something with two B's,
there's no distance to A, B, because you can't delete a B. You've got to modify, turn this into a function. It's just a one-off function, but the point is the initial condition and the anchors are related. So
yeah, okay, but let's just put string reverse of, let's just do this. This will be, again, so this I claim will be Let's
You've
just
got to
make
crank
this
that up.
big. Yeah.
Make it big.
It's a grid, I think, some kind of grid.
Mm.
Because we see we
I
don't
think
want
it's
to
a
make that too big because otherwise we're confusing ourselves by what the distances are. Actually, we don't know what the distance, we don't know what the other natural distances are. So let's say we say, oh boy, 0.5. I'll tell you what we can do here is say states graph structure. At least then we'll see the structure of the thing.
Oh, nice. It looks very much like, it's like every step it alternates which neighbors it connects to, which looks like a hex grid.
Something
In
like
fact,
that.
Wait a minute. I mean, this looks like the branchial graphs that you showed with A's and B's. It was also with A's and B's.
Yeah.
Remember?
Yeah, but this will also be I mean, this is ultimately the graph that you get. Look. It's something related to that, isn't it? That's the graph. That's just the structure. I think it has to be related to this.
Okay. Well, then the symmetrical anchor points, I mean, we just happened to pick 2 anchor points that were obvious, but there are 2 other anchor points which are obvious, which are the ones in the middle at opposite ends, right?
Let's try that. Okay, so what
which
do you
are,
say?
I think, opposite. It's like they would be opposite parity. I guess they would be. Can you just look in that picture that you had there in the just above? Yeah, I mean, you did structure, so we didn't see exactly what they were, but it would be.
What are you suggesting? You're suggesting these ones in the middle?
Yeah, no, well, good. Sorry, just go down. The structure graph that you plotted.
Yeah, this one here.
Yeah, yeah. So in the middle, the top vertex and the bottom vertex, those are also the natural.
I see.
Natural anchors, and I don't think there are any other natural anchors. Ah, 2 B's in the middle and 2 B's on the sides. Okay, I mean, that's obvious from symmetry.
Oh yeah, B's in the middle and B's on the ends. Okay, hold on. So B's in the middle is AAA, BBAA, and then oops. Okay, what's going on there? All right, let's not do the states graph structure. Let's just do states graph. Okay.
That's fascinating.
Okay, so this is distances from the 2 B's are together, and this is going to be distances from that guy there.
What about 2 B's on the far left? I'm not seeing that anywhere. Where is that? Oh, it's right underneath the 2 B's on the far right.
Oh yeah,
I see.
but it's not really. I mean, it's right underneath because it's a. I mean, that's because hold on, it's degenerate with that. I mean, that is
it's degenerate, yeah. And fundamentally, this is telling you something that graph distance will never understand, which is that there are actually 2 opposite directions here, but the distance increases positively in both, right? So it's 0, 1, 1, 2, 2, 3, 3, 4,
Oh, I see
4.
what you're saying.
But if it knew more,
well, that's because it's a directed. This happens to be undirected because we got arrows going both ways. But let's understand here. If this is our coordinatization, what theorems are obvious from this coordinatization? Right, so in this coordinatization, you know, there are things which are related by the partial order.
String reversal, by the way, gives us the duplicates.
Yes, but look, what I'm trying to understand is what can we learn by looking at coordinate positions? So the claim would be, and we have a choice. We can either go prove a theorem by just tracing our way through this multi-way graph, right?
Mm.
Or we can prove the theorem by first setting up a coordinatization and then just looking at that coordinatization. Right? So what's an example of where there is an obvious theorem based on this coordinatization?
Well, here's an obvious thing, which is that if two things are far away in this coordinatization, they have to be far away in the regional graph.
Yes, that's true. Yeah, but I'm trying to understand. Look, one feature of the original graph, wherever it was, is, yeah, this graph is actually a lousy example, because a more interesting case is, let's see, how do we get from, I'm thinking about sort of the everything in this graph is equal to everything else. There's a path from everything to everything.
Yeah.
Right? Which is in a sense not a particularly good model. You know, I'm trying to understand, and maybe that's why, I mean,
so
yeah,
maybe
if we
want a bit of directedness.
Well, either that or we want something which isn't simply, you know, is not simply making us identical things. We want something where there is directedness that adds novelty in some way, like just adding in generators. Am I making sense? So if we just added in generators here, okay, what would happen if we just added generators to this? Then does that give us something where in a sense, the directed paths, I think it does. I think it does. I think if we add those in, then the directed paths become then we're generating all possible, yes, I think that's right. I think we can do that. Then directed paths become the true theorems, so to speak. And these undirected pieces are just equivalences between these. Does that make sense? So if we add to this the notion of appending elements to these strings, right?
Mm-hmm.
Then the claim is, and that's what I think Jonathan's code was doing. Go back here. Wherever it was. Well, let's see. Do we want to do? Let's do multi-way semigroup. Okay, so the claim is that here. Okay, so this is with the novelty generator. So this is a semigroup now. Let's see. So, for example, our abelian semigroup, which is what we're looking at here, includes the relations AB goes to BA, BA goes to AB. Okay, so this, as you correctly observed, they're really two kinds of arrows here, which we really should
be helpful to. Yeah, exactly.
Is there an obvious way to do that?
Well, you have the original code, right? It might be.
Yeah, sure I do. Let's go change it. let's see, multi-way. I've got the original code here. Okay, multi-way semigroup. There we go. Okay, all right, so let's say, oh, this is completely crazy, this two-stringing stuff. Well, let's just get rid of the two strings. Well, we're just going to assume that everything is a string. Doesn't matter. Okay, so here, generator rules, relation rules.
So the problem itself is that multi-way system can't tag. I mean, seems like a decent feature of a multi-way system to have. But some
It does, but we can do it as a post-process. Look, we can easily do that as a post-process thing, can't we?
How would you know which one was used? What is edge list of this thing? It's just the edges they're not labeled.
Let's think how to do this. Well, I mean, as a hack, in this particular case, anything that increases the length of the string is a generator rule. I mean, that's total hack.
No, but you can do an edge shape function that just looks for that. That will be easy and it'll draw differently.
Okay, can we do that? What do you know how to do that?
Yeah. So it's just so you're gonna take that, and it'll be easier to do it as like a little post-processing function rather than redefine this whole function. So it would just be takes the graph, calls graph again to overload to change an option, and the option it wants to change is edge shape function.
I thought that was a deprecated. Okay, that's not a deprecated function.
And then function again, capital F function. And it takes 3 arguments, I think. One is let me just double check, edge shape function. Yeah, so the first thing is a list of coordinates, so coords. And then the second thing is V directed edge W, like pattern. So you can't destructure it inside the function, because function doesn't support destructuring for some reason.
Yeah, okay, so you're talking about
edge, put edge there, yeah. And then you need only say, if string length first edge.
Wait, what's the third argument of the function?
There's no third argument, I was wrong.
Okay.
So then just say, if string length first edge greater than string length second edge, or different from, I guess.
Well, let's say if string length, the first of edge is less than string length of last of edge. And this is a hack alarm.
The problem is that there's 3 cases. There's if they equal, it's the one kind of relation. And then for one side or the other side, then you have to.
No, for this case, the only case of interest is it got longer, which means it's
yeah, sorry, my bad. Yeah.
Okay, so now what do I say here? If this, then what?
Then arrow of coords. So, but you can pop the style on there, right? So.
What do you mean?
So what this thing should return is an arrow of coords. But then you're just going to attach a style based on this property, right? So
it's just arrow of coords with style of arrow of coords or something.
Style of arrow coords. So you could pull the arrow out the if statement, for example.
Yeah, I know.
And then have the if. Yeah, exactly. That's perfect.
Okay, so style arrow coords. If string length red, then otherwise blue.
Close the bracket for arrow.
close for the if, close for the style, close for the function, close for the graph.
Mm-hmm.
Okay, so that's saying that, okay, that looks fairly convincing. So this is mostly a generator game in this case, right? This is mostly just lengthening things.
Yeah.
But here, oops.
So there's an obvious feature that multi-way should have, I think, which is to attach different weights to different rules. And then the budget that you set is relative to a weighted total.
Yeah, that's a good
Because,
idea.
for example, because we want to focus really, we don't mind having generators, but we don't want them to predominate. So we prefer to weight up.
Now, actually, we have that kind of thing in the Wolfram model function. In Max's Wolfram model function, it has pretty elaborate termination conditions that are along those lines. Okay, so let's just do color, G color, let's call it, of G blank. Okay, so now it's G color of this. Okay, so the core of that thing is those relations. And then there are a bunch of things. Okay, so now let's make this a layered graph. Okay, that's kind of nice, actually. So what the layered graph is doing, oh, that's kind of weird. Look, with no relations, what is this doing with no relations? If we had no relations here, what is that? That's just...
Well, all things are generated.
No, I realize
that.
But that object is, I mean, the fact that it's a causal invariant creature here.
It's because adding things on the left and adding things on the right, you end up with the same thing.
Oh, that's a good point. Right, but if we only add it on the left, so we get this causal invariant structure because we're adding on both left and right.
Yeah.
But we get the same basic idea by just adding on the right, I think.
Yeah, in fact, it seems wasteful to add on both sides because any sequence of A's and B's will eventually be created if you only add on the right. You're just,
sure.
You're just mixing things. You will have twofold redundancy, right? If you do both.
Well, let's just edit this code. Right, so this code here, let's call that in my 1980s way, multi-way sum group X, and let's say generator rules here. Okay, there are the generators. Okay. Generator arrow.
That's joining on the left, I think. My God, I don't find this code easy to read.
Well, let's just read it. Hold on one second. Catenate.
I mean, this is a table. It's a two-dimensional table. It's a table of gen goes to string join gen. I goes to string join.
Why is it going that way around? Why is it doing it both ways around? I mean, it just has to append on the right.
Yeah, I don't know.
Let's just call it right here. Okay, look, generator equals hash, generator. What?
Yeah,
What is the difference in string generators? Oh, I see. Oh, this is doing something completely crazy here. This is because he's got separate, okay, everything should be string generators here.
okay.
We don't want anything that isn't a string. So we're okay by just saying, so generator rules, I claim.
Can you echo that so we can at least see what it is?
Yeah, okay.
So group right, yeah.
Okay, A goes to AA.
No, that's way too, that's incredibly redundant because all you'd want to do is just add it to the left of the entire word, surely.
I think so, but there's no way to do that with these generator and relation setups.
No, you can just say end of string, arrow, whatever. That's a string pattern.
Is that going to work
right?
in multi-way system?
I mean, if it doesn't, then that's a bug.
Right. Well, okay, let's try that first. So let's say, okay, so let's say end of string goes to A. I'd be amazed if this works. I bet there's going to be error checking code that gets
Actually,
this.
multi-way system seems to not check for errors. It just doesn't evaluate.
Okay, well, anyway,
so
let's try this thing here. AAB, let's say 2 steps. Splaff. Okay, it would be nice if that worked. If we can make that work, then we can make this thing work with generators in a good way.
Because the thing with this is it explains why it was so generator heavy. Because I guess to work around this thing, that problem,
right. It's working around this problem. It's just having these relations that are just a very, very inefficient way to
they're very promiscuous. Yeah, they're matching everywhere they could possibly match.
Right. Okay, but this but this layered graph is quite nice because this layered graph, if we look at the bigger version of this layered graph, it's probably got a lot of okay, so the core of this is the actual relations. Oh, Nick on our live stream is suggesting that we put an X that's at the end of the string. Will that work?
The problem is, well, yes, the generation rules would then just have to replace X with LX and AX and BX. That would work.
Then we'd have X's all over the place, but that's okay. That's a harmless problem. Yeah, that's not a bad problem to have. Okay, yeah, that's a good idea. So we can a hacky way to do this, hacky approach, just have an X at the end of each string.
Why don't you do that? I mean, it's so.
All right, fine.
It'll take us 45 seconds.
Okay, so fine, let's do it here. Okay, so what are you suggesting we do? You're suggesting that we put.
So step 1 is that the multi-way system call at the end of the function.
Right, I want to rewrite this. Hold on one second. I want to rewrite this to not have all this insanity with strings. Okay. Let's just get rid of that whole idea. It's just generators. Okay, so there's no string generators here. There's no string relations here. Everything is a string.
Yeah. And then the generator rules are merely thread X arrow generators. Well,
Thread.
a little bit more.
What?
A little bit more. It's thread X arrow. Well, rather do it as a map. X arrow hash string catenate X. Do you know what I'm saying? Hash less than greater than.
Yeah. Hash.
And then X again.
X. Right. Map that over generators.
Yeah.
And then thread that.
I think that's it, actually. You don't need anything more than that.
I think it is.
So,
hold on.
And then another thing gets simpler too, which is the initial condition for multi-way system is just going to be X, which is nice.
Indeed.
And in fact, don't use X, use space, because then we won't even see it.
We could use thin space.
You could use thin space. There's probably some like invisible space or something. You could
There is an invisible space. We could use invisible space. That would work. I mean, it will confuse other things, so let's not do that. Okay, so here. Okay, so now what do we do for relation rules here?
I think that's fine.
That's it. Yeah, that's the correct thing.
That's
string relations becomes just relations.
Yeah.
And why do we need? Oh, we need delete duplicates in case something is repeated there. Okay, so let's try this now. For our original guy here.
Yep.
Okay.
Yeah, it's going to be a binary tree.
Right. So this is now the free. Well, this is essentially the. Okay. So this here is the free semigroup. Right. So we can go. Let's go 3 steps in the free semigroup. Notice that this is actually also the Cayley graph of the free semi. It's some kind of Cayley graph-like thing for the free semigroup.
Yeah, and that's because the only edges are edges from generators.
A generator.
Yeah.
Which is exactly what we want. Okay. All right, so now let's add some relations to this.
I think that gets handled, by the way, that redundancy where you do it both ways, I think that's already happening in his catenate. You see that? It's doing the both ways there already. So you don't have to type it out, just for the record. You can just do AB goes to BA, and that's enough.
Okay.
Convenience feature.
Okay, so is there a way, using this X array, is there a way to deal with the coloring? Can we use the X? Does the X thing give us any clue about the coloring? The space thing give us any clue about coloring?
No, but the length trick will still work.
No, I understand it will in this case. Right.
I want to point out, that there's a graph theoretic object that's missing here from maybe not Mathematica, but it should be a resource function, right? Which is, we would definitely want to tag edges with the relations that produce them. And that's something that multi-way system should support directly, right? That it remembers which rule produced which edge. But then we want something else. We want to collapse a graph by modding out particular edges. So we want to say we're going to take all edges of type X and mod out vertices that connect via
Yeah, right,
that
I understand.
edge.
There is a tagging mechanism. In 12.1, there is pretty good tagging of edges. Although I have to admit, I haven't used it.
I saw that.
Right.
That would be nice. It would be nice to take advantage of that for the modding operation.
Right, but the main point is that multi-way systems should be able to add edge tags.
Mm.
Okay, so let's just do our coloring thing here. So this is, okay, and let's do a layered graph plot of that. Okay, what are we learning here? So this is now, these arrows are rather ugly, but let's try going 5 steps here.
Why don't you do line rather than arrow? Because the truth is time already gives us, we know that arrows point down.
No, we don't.
Except for
these arrows here.
But the relations are symmetrical always. So we don't need to know which direction they went.
All right, fine.
G color.
Yeah, I'm going to do a,
cool.
well, let's do a structure, states graph structure. Really, what we probably want to do is to make, actually, let's do this. Let's make those dotted versus, let's say if string length is less than that, then make it dotted. Otherwise, make it red, let's say. Well, let's keep it blue. I'm actually going to...
Do you know what would be fascinating for, and it would make all of this stuff quite trivial to do, is if the metadata of which paths produced a given state was captured, like which sequence of replacements produced a given state was captured in
multi-way system.
In the multi-way system. Because then what we could do is, for example, the binary layout of this thing, that should be the predominant layout. And then the relations, do you know what I mean? That, because the sequence of generators should give, that is a coordinate scheme right away. And it'll make it nice and binary.
Take this object here and coordinatize that using our coordinate system thing, right? So we should be able to take our graph coordinatize 2D, right? On this. So graph coordinatize 2D of, well, let's call this GX1 for no particularly good reason. GX1, and now, what do we want to do to coordinatize this thing? We could say, let's take, I don't know what we want. But this won't necessarily even have a graph distance, will it? Between one, because this is a one-way graph. So this coordinatization is no longer going to work.
I mean, the thing that is appropriate is my original idea, which was coordinates counting the number of generator applications. In general, any rule application, but.
Yeah, right. Okay, so, okay, but anyway, could coordinatize by number of rule applications.
In fact, we can recover that from the vertex. It's just string count of the vertex and then A. list A comma B, because I think string count will list itself. So
sorry, so that was what were you just saying?
So if you say string count of the vertex, which is a string, comma A, that'll tell you how many A's it has. That's
Oh, I see. That's going to tell us how many. Well, just the string length will tell us how deep we are in this picture.
Oh, yeah, exactly. Yeah.
But look, I want to come back to the original objective here. So this is a sort of exploration mechanism. So the theorems of mathematics. This is a novelty generator for mathematics in addition to a theorem finder, right? Which is something a little bit different. I mean, a theorem finder would just say the theorems correspond to paths in these components, right? And effectively what's happening here is if we were to Cayley graphify this, every one of these components would be crushed to a point.
Yeah.
And what we get left with is the rest of the structure would then make the Cayley graph. So for example, we could look at the Cayley graph for an abelian group just for fun. And what we should be able to see in this thing here, we should see these lumps of area which correspond to the relations in the group, together with just sort of the generation of novelty in the group. But I'm still. I mean, I want to come back to the original objective here, which was. The original question was, okay, so a model in these things would correspond to, I mean, this is, we didn't do it here, but we could coordinatize this. That's what we did earlier.
Yeah.
I'm still a little confused by this. What would it mean? So if we coordinatize this, and then what would the coordinates do that would allow us, because here's the big picture. The big picture is you have a choice. You can deduce things from coordinates, or you can deduce things from following edges in the original proof graph. That's kind of the concept.
Well, the hope would be that, and I guess the claim would be that coordinates always represent some kind of pocket of computational irreducibility that you've used. I mean, coordinates are just one kind of reduction, right? But they are a reduction, and
yep.
They're explicitly in an abelian group structure on some slice of the
yes.
of this thing. And they allow you to shortcut things. I mean, they're not the only kind of shortcut, but they are probably a very powerful and common kind.
Right, but another shortcut is one of these completions. I mean, that's another type of shortcut. That is a particular, a jump ahead lemma, so to speak, in this system. So, I mean, again, but back to the sort of big picture of what one would like to understand about metamathematics, because that's kind of what part of the objective here is what is the the goal is what do Einstein's equations say? For example, they say a geodesic is deflected by the presence of causal edges. Okay. What is a causal edge in this case? A causal edge is presumably that a particular lemma, well, a causal edge is a relationship between results that you got at different steps. So to say that there's a causal edge.
Well, remember, there's always the long way around of doing things. We don't have any lemmas, right? But if you compress chunks of mathematics away using lemmas, then you're necessarily introducing little shortcuts, little wormholes. Those causal edges introduce curvature in the mathematics that you experience, right? Okay, that's very vague, but
yeah, I think that's right.
But it's fundamentally it's an observer effect. It's not that it's really there. It's that it came because you wanted to shortcut things, because you wanted to compress your proofs.
Well, arguably, that's the same thing as saying there's no, you see, but that's the problem. There's things that you get from coordinatization, and there's things that are intrinsically there. And what's the trade-off between those? And the answer has to be, with some underlying axiom system, there is intrinsically curvature in this metamathematical space. With another axiom system, there isn't intrinsic curvature. There is merely coordinate. You can have a coordinate system that doesn't have a flat metric, so to speak.
Yeah. But surely that's what you would expect, because by introducing, you can always introduce a lemma or a completion or whatever. I don't know.
No, but wait a second. I mean, the issue is, what is the analog of do you get what I'm saying? Well, the question is, what's the analog of the result?
Well, there's a phenomenon that I know about from black holes, right? Where there's like a fake horizon that's not real. It's just
that's
coordinate singularity.
Yeah.
So are you saying something that relates to that?
I'm saying that you can have all kinds of crazy coordinate systems, but they don't have genuine curvature.
Yeah.
The genuine curvature, I mean, we can perfectly well measure curvature. Look, an example of this, okay, if we take I'm just looking up oh gosh, what is this now?
But Stephen, so I mean, general group, let's say like the free group on whatever number of generators, right? There's no unexpected connections there. By definition, that's what it means for it to be free.
Yep.
But then you have some model that's not the free group, but the free group certainly maps onto it. And then you do see weird identities that shouldn't be there. And isn't that what we're talking about? Isn't that a very concrete instance of curvature, meaning, like, I would say there's torsion, like you go in this direction, you go in that direction, and you actually ended up at the same place, even though you shouldn't have, just from a pure coordinates point of view.
Yes.
That's something real, but that's produced by a particular group, the particular group that you chose, not the general free group. And in effect, that's curvature introduced by the relations that you added, right? That's exactly what we're talking about.
Yes, I think so. So you're saying, I mean,
and it's even called torsion, like a group with torsion.
Yes,
that's a particular kind of relation you can add.
Right, but so your point is, the presence of those extra axioms goes from having a flat space to having a non-flat space.
Yeah. When your coordinates are the generators, the counts of the different generators.
Right, but the question is, to what extent is that a, quotes, coordinate singularity, and to what extent is it something real? And so just to remind us, in these proofs, okay, so this is an attempt to represent a single path proof. The only difference here is that there are these dashed lines that represent the dependence of a lemma, the reuse of a lemma. So
The triangles are lemmas.
The triangles are lemmas because the triangles are branch pairs that were turned into lemmas.
Okay.
So in other words, this is a place, if we look at the original multi-way system, there will be some part of the multi-way system that is just single way, okay? Every time it might have branched, this says, I'm going to add a lemma to represent that branching.
Why does one do that? This never made sense to me in Jonathan's explanations. I don't know why that's an important part of the technology of theorem proving.
Because remember, well, let's think about it. What is the theorem prover trying to do? A theorem prover is trying to find a path through this multi-way graph, right?
Mm-hmm.
So the question is, how do you find a path through the multi-way graph? And this is a trick for doing that because every time there might be we could have gone one way or the other, right? Add a lemma that says those two ways we could have gone are equivalent.
Why do you get to do that?
Because whatever the two branches were, you know they're equivalent. Because let's take two branches from one of these previous things, right? From one of our things where we're just looking at the equivalence case. You get to do that because let's say this branch and this branch here, they're equivalent because you just derive them both from the same thing.
Mm-hmm.
So you know they're equal, right? You know that this is equal to that because both were derived from this.
Okay.
Right? So what that's doing is it's saying instead of worrying about which branch to take, just collapse the two branches together.
You do that immediately or do you wait?
No, you do it immediately. You do it immediately. And then I don't know which one you do it immediately. That's okay. So what's happening here? You collapse those branches and then let's see, given that you collapse the branches, you keep going. I mean, there's something a little confusing about this because we need to, I think, these pictures were drawn long before we understood multi-way systems. Well, actually they weren't. They were drawn after I had understood multi-way systems, but before we'd understood multi-way systems in the context of this project. But the point is that each one of these is a branch. You can follow either branch. But then you have in your bag of tricks, you have that lemma now. And you reuse that lemma later on when it applies again. Now, there's still a question.
Okay. So maybe an analogy that, it's just occurred to me, but it's like kind of like spontaneous symmetry breaking. You know that it's got to be something. You haven't found the proof yet, right? You know that it's got to be something. And there's might be total symmetry in which thing you expand first. And you just know that one of them is going to work. You just don't know which one. And you expand one of them and just assert the symmetry among all of them at that point as a lemma.
Yeah.
With the hope that you'll be able to undo the symmetry breaking later via that lemma that you introduced. That's as an analogy that might help me think about it.
Right. I think this picture is essentially, this would be one path through the multi-way system, but for the fact that there are stubs here that are stubs of things going off in the essentially branchial direction. This will be a single time-like curve with things, plumbed into the multi-way system where these branch pairs correspond to alternative branches in the multi-way system.
I would love to understand this better, because especially the Boolean algebra quality of it seems like a powerful way of thinking about multi-way system branches, right?
Yes. No, actually, Max had just mentioned to me yesterday his realization that branch-like, space-like and branch-like are like DNF and CNF. So branch-like is like ORs.
That's cool.
Right. But so in this picture, so the question is, in space-time, effectively, in our metamathematical space-time, we are looking at a path. We're modeling mathematics as being a bunch of GD6 in metamathematical space. By modeling mathematics, I mean we're assuming that mathematicians are maximally smart and get maximally short proofs, which isn't correct. But let's assume it was correct. Okay? Then the question would be, what is the relationship, for example, between those proofs and sort of, one of the possible ideas is there's a notion of accumulation of lemmas which come because of branchings. Well, I'm not sure. I mean, there's an accumulation of lemmas that you're going to use later. You could have a field of mathematics where there are no useful lemmas that get built up. There's a field of mathematics where every theorem, I'm not sure if this is right. I mean, I don't think it can happen with strings, but I think it could happen with arbitrary expressions, where you essentially just have a single GD-SIG.
Okay.
But so the bigger picture potentially is you've got a field of mathematics where you have built up a bunch of accumulated lemmas.
Mm-hmm.
I'm just trying to understand what is the form of, the form of statement that we would expect. Assume there's an Einstein's equation in metamathematical space. Basically, the statement is going to be geodesics in metamathematical space are deflected by the presence of accumulated lemmas.
But I think this gets back to the struggle that we just had, which was to what extent, when is curvature intrinsic and when is it merely a reflection of a coordinatization, right?
Possibly so. Yes, possibly so. But I think the coordinatization, what appears to be the case. See, the confusing thing here is, the coordinatization could be thought of as, what is the relationship?
Funny idea.
What's that?
I had a funny idea of like a powerful theorem as being like some very heavy object that gravitationally lenses distant theorems, right? Like it should be hard to see them. They should subtend the small.
Idea. Yeah, okay, all right. That's a cute idea. Powerful theorem corresponds to high mass gravitational lensing object.
Right. But the point being, I guess, that we can see further because of it, right? We can reach more distant theorems.
By virtue of the fact, well, in a sense, it's reducing, I don't know whether it's that's very confusing.
Maybe it's
no. I think it's the opposite way around, actually, because what you really want is, any one of these. Look, there's this notion of jumping. As you add a lemma, you get to jump through. Gosh, this is confusing. I mean, look, I think.
But look, as a model for what makes like if you have less respect for mathematicians and you imagine them doing something that often amounts to a form of random search, whether they realize it or not, then really what makes good theorems is just that if you do random search near them, you end up in useful places, right? Like they take you further. They make your random search more effective. I guess that's the connection with gravitational lensing. It could be that like the big important proofs that we come up with are often pretty arbitrary, but because they exploited something powerful, they're kind of bent in the right direction to get to a useful result.
But the thing I'm curious about is what is our conceptual way of thinking about? So there is mathematics as it has been practiced. There's, that's the solar system that we've explored, so to speak. There's the complete universe of possible mathematics out there. What kind of a statement can we make about the complete universe of mathematics that's out there that is analogous to statements about, I mean, it does help that we get...
What's the cosmological constant?
Yeah, well, okay.
There's all of mathematics curved.
There's an important point about the universe is that we have photons, for which time does not elapse, but they, propagate. They allow us to be sensitive to things that are happening elsewhere in the universe in a way that it's not clear there's any analogous thing. In mathematics, we've only been. See, this is the claim. This is the sort of this partial claim that we're making about non-constructive proofs corresponding to light-like propagation. That
what is the claim?
The claim is that if you try to foliate one of these systems, you can only do it with sort of finite slope. Not finite, with a slope less than the speed of light. So there's a speed of proof, right? In any of these pictures, there's a kind of notion of a speed of proof, which is how fast the light cone of proof expands. Right? I mean, you can't reach things. There's only a certain rate at which you can reach new results, new expressions. Makes sense?
Well, why is that not tautological? I mean, it's one edge length per edge length. Why is that not tautological?
Because there's a notion of space as well. Because
what's the notion of space?
Because this knits, like that guy there is not close to this guy here, because there has been at least there's a branchial space here. There's a notion of space in a branchial sense.
Okay.
Right? So in other words, it's saying that there's a maximum speed if you're trying to get, let's see, if you wanted to know like a common successor of these two things would take a while. These two theorems, which are separated, these two expressions separated in branchial space, will take a while to intersect.
Mm-hmm.
Right? That's the statement that there's a maximum speed of proof. Which would also be, if we look just down a time-like direction, we'd also have the same effect.
Can't I introduce an axiom or a lemma that just says BB over there,
oh, absolutely,
AB over here, and then there's zero distance.
You can, but you can't introduce a lemma that's incompatible with the original partial order defined by the original axioms.
Mm-hmm. Agreed.
Right? And that's the thing that one is saying, is that one can't introduce. That's why there's a limitation on what foliations, models, lemmas one can introduce. The claim is the deformations one can make to this picture by adding lemmas, by adding valid lemmas. There are limited deformations one can make to this picture by adding valid lemmas. And the claim is that there is a notion that, for example, if you try and add lemmas, well, what happens if you add lemmas? Okay, if you add equivalences that are essentially space-like equivalences, like you would do in simultaneity in space-time.
Mm-hmm.
That's like adding, additional relations that go from general groups to a specific group.
Yeah.
And that's a lemma you're adding that essentially is giving new information. Yeah, right. That's the important point. That's the important point. That you can add a lemma that gives new information that you didn't have before, that says this is actually equivalent to that, right? That's the important point. I mean, you can add lemmas / relations that give new information, but they have to be consistent with the underlying axiom system.
Yeah, which is another way of saying, like you could say, oh, these things called abelian groups, but it turns out that actually there are no abelian groups. You could imagine them, but they don't exist, right?
Exactly.
But
yes.
Of course, we know that there are abelian groups. So.
Right. Right. So it's giving new information that wasn't there before. So that's what it means to have a model, is to make equivalences between things that weren't equivalent before. Now, those equivalences could violate the underlying, right? The equivalences could violate our underlying set of relations here. Now, the claim is that this constructiveness okay, so the potential claim is, okay, what is a model? What's the point of a model? The point of a model is to say, I know there are all these constraints, but the thing that these constraints are leading to is actually a thing that we can talk about. So, for example, the integers or something, right? There's a set of constraints, but the set of constraints is sufficiently rigid that it actually lets us talk specifically about the integers. It actually forces us to be talking specifically about the integers, or specifically about this particular group. I mean, I'm not really as familiar in group theory. As you go from the main axioms, from the abstract axioms of group theory, and you start adding relations, okay? The thing people most obsess about is the finite groups.
Yeah.
And then if you add more relations, you'll get some subgroup of the finite groups, et cetera, et cetera, et cetera. But I think what you're doing is, essentially it's just saying you're adding relations, you're getting subgroups, basically. Which is,
yeah.
And at some point, you get to the point where you have, for example, a finite group, and then you might say, I don't know whether you'd say it's about anything or not, but I had this plot in the NKS book. That showed this was the extent to which an axiom system is about something. So this shows the possible multiplication tables for, like, the axiom system B dot B equals A has no multiplication tables consistent with it. So some axiom systems have, like, A dot B equals A has these multiplication tables consistent with it of size 2, these ones of size 3, and so on.
That's cool.
So the argument could be that, I mean, it's a wrong argument, I think, that fields of mathematics are really about something when the set of possible multiplication tables is, just one multiplication table, for example. Right? That's what it means for it to be about something. And so, okay. but so, I mean, again, I just want to come back to this question because I think we're actually slightly close to being able to have a reasonable answer to this. We've got, the question is, what statement could one imagine making about sort of infinite metamathematics? So, for instance, here's a type of statement one could make. Okay, so this was the kind of thing we were going for a couple of sessions ago, is this notion of constructive proofs being ones that were created by making models, where the proof follows from the proof follows just from knowing things about the model without you having to trace all the individual pieces. And okay, so look, the big claim I was going to make at the very, very, very beginning of this was the surprising thing about physics is that it's possible, as in the surprising thing is that one can that one doesn't have to follow every micro detail of the universe. One can make these global statements that come from relativity and quantum mechanics. And so the question is, in mathematics, what's the analogous statement? The analogous statement would be, you're not mired in, you don't have to go down. Well, you're not mired in undecidability, which is probably related to, you don't have to go down to, I don't know how that's related to the question of whether you have to go down to the sort of irreducible level of having to go sort of step by step by step, unable to use lemmas, so to speak. I mean, maybe the analog, what the heck is the analog? See, the claim would be that.
Well, can I take a quick crack? So
yeah,
and I'm also getting pretty sleepy, so I'm probably not going to be very
right.
useful.
No, we should wrap soon.
But
go ahead.
But so from, like, I'm quite keen on the idea of coordinatization as like an important part of the puzzle.
Mm-hmm.
And in that picture, it would be, I guess, the surprise is that mathematics is not riddled with singularities, like coordinate singularities, where you just can't say anything beyond a very short distance away. There's so much curvature that, like, your coordinates get scrambled and become meaningless, right?
Right.
But they're tracts that are useful, and that maybe that there's some scale involved, that you can zoom out a little bit and there's a coordinate change you can make, and suddenly you can talk about a new kind of more abstract object than before, and things continue to work at that new scale. Maybe that's my version of what you're saying.
Well, you're saying
that there is space, right? That there is some kind of the things limit to some kind of space in enough parts of mathematics that groups, for example, have examples that aren't just tautological, that you find groups in other parts of mathematics.
I see what you're saying. So you're saying that the fact that this thing could limit to a space rather than being full of singularities all over the place.
Well, the claim is that group, like for example, the idea of a group is a particular kind of coordinatization that shows up in all kinds of different axiom systems. In other words, there are models of groups all over other parts of mathematics.
Yeah.
And that phenomena of mathematics being able to describe itself is quite common. That if you look at one part of mathematics, you'll see other parts of mathematics in a sort of fractal-like way. And that is a claim about things not being so incredibly intricate and textured at any place in metamathematics that there's just no coordinatization there that lasts for very long.
Well, you're claiming that there's a, okay, so the claim would be there is a reasonably uniform coordinatization.
Or patches of them, right?
Okay, well, yeah, okay, right. Or patches in metamathematical space. And the implication of that you're drawing
is that, well, for example, there's computational reducibility. Right?
Sure.
That things like groups show up in other parts of mathematics, and they're not just vacuous descriptions of themselves, right? But you can apply them elsewhere.
So, I mean, my logical thinking, my logic for all of this was the following thing. Okay, in physics, of all possible rule systems, there's underlying irreducibility. But the point is that the aspects of the behavior of those rules that we observe are ones that have been bucketed by the fact that we are computationally bounded. That is, we're not able to, we always create these equivalence classes and look only at the behavior with respect to the equivalence class, not at the behavior with respect to the very most underlying thing. And the speculation was that in mathematics, the way that we choose to do mathematics also does that kind of bucketing, probably through these extensionality axioms.
Footnote, because I don't know what extensionality axioms are, but yeah.
Okay. But I mean, they're just these axioms that say that they're like the univalence axiom and so on. They're axioms that say things that are equivalent can be treated as identical.
All right. So what's his face's identity of indiscernibles? Leibniz.
Is that right? I don't know that. Okay. Yes. Okay. That makes sense. Okay. I'm not surprised Leibniz was onto this particular thing. I need to look that up. You know, I have this idea that the question is whether philosophers who said things that now seem obvious were saying things which were always obvious, but you know, and that's why they're significant. What's that?
Yeah,
or whether
we got
they're
lost
only
or
obvious
something.
now. I mean, there are plenty of things that look like computational irreducibility. I think is obvious now, but it wasn't obvious when I was first yakking about it. So it's so maybe I've got my own. Okay. In any case, the
By the way, I do think it's a wonderful thing to think about, and I've enjoyed thinking about it a little bit. That like we all have our own, I guess, intuitions, and what are the things from the Greek geometers? We were just looking at him. Sorry,
Euclid.
Yeah, Euclid. Euclid's whatever principles or whatever he concept. What?
Postulates, common notions.
Postulates, common notions. Yeah. So like we all have our different versions of that, and you can see, I guess, you can see those as some kind of coordinatization. And so things that are hard for things that seem obvious to you might have been completely alien to the previous generation of physicists or mathematicians or whatever. I mean, it's an obvious statement, but
no, it
I
is.
like
But it's also, but it's an interesting statement because that's that's this whole issue about alien intelligences and their view of physics. Is what, with different, but my current logical thinking was that mathematics is doable because we implicitly assume certain axioms that cause us to bucket things in the same way, in the same kind of way that we bucket things in physics that lead us to things like relativity and quantum mechanics. So your basic point, okay, so I'm going to make a claim. Mathematics is in practice doable. And it's the same because you can reuse lemmas and so on that you've used before, that you don't have to reinvent, everything every time you reach a new part of mathematics. You just can use a bunch of things you already knew to make progress there.
Mm-hmm.
Which is, I think, the same as, it could be the case that every new place you reach in metamathematical space
demands its own unique coordinatization or set of lemmas or whatever.
Right.
With no relation to anything else, no intuition to go on. You can't do any parallel transport of your ideas from the spaces from which you came.
Right. So that is a statement that, mathematics is comparatively. So the reusing of lemmas you claim is a bit like parallel transport.
Perhaps, yeah.
Perhaps, not clear. But
but there's an interesting point that, hold on, Stephen, but this connects back. There's a nice way of completing it back into your whole oeuvre, which is that that's just the parts of mathematics that we've had any ability to crack. So like people have just been scared off from all the shit that was just impenetrable forest, right?
Mm-hmm.
And that impenetrable forest is by definition computational irreducibility manifest, right?
Yes.
And so there's this, it's a silly kind of, the kind of argument where it's like, oh, we exist in a universe.
Yeah, anthropic argument, right.
It's an anthropic argument applied to mathematics, right? Like, of course, mathematics has been successful enterprise, and that's just definitionally so, right? The only puzzle is that any parts of it were reducible at all.
Well, I know, but that's the statement. That's the thing I've been claiming for ages. But the thing that I'm trying to understand now is it the case that, the thing that I didn't know 3 or 4 months ago, 6 months ago, whatever, is that physics avoids computational irreducibility. That the physics of the 20th century found a way to skate on top of irreducibility. That's the surprise. And so is mathematics also somehow skating on top of irreducibility?
How could those things come from a common place? Those seem to be the clearing in the forest in both cases. How could that clearing derive from some fundamental principle? Isn't it just an anthropic fact, right?
No, I claim it is an anthropic fact, but I claim the reason it's an anthropic fact because we are computationally bounded. That the only thing you need to know, in other words, the logic is we are computationally bounded implies we build a physics / a mathematics that we can do. Okay, now it might not be possible. It might be that we're computationally bounded and we're toast. Doesn't work. We can't figure out anything about what the universe is going to do or about what mathematics is going to do. But this fact that we can build, this might not be possible. but it is. And the claim is it is because of something to do with causal invariance.
Oh, okay. There's the payoff.
Right, right. So this might not be possible, but it is because of causal invariance. And now the claim is, I mean, so Jonathan has been making this claim that everything flows from the infinity groupoid, which has a certain, I don't know, it's a
Cachet to it, perhaps.
What's that? No,
but I think
the infinity groupoid is inevitably causal invariant.
Okay.
So
I mean, that might be a very elegant way of capturing something that can be developed in more English terminology, right?
Right, but I mean, but to say that there's, it says that in the everything model is causal invariant. When we take sort of fibers from the everything model, there's a question of how much of this causal invariance do we inherit? But it could be that we can always get enough of it back. So I mean, I think this is the logic. We're computationally bounded, and there's a certain that causes us to look at only certain kinds of things in physics and in mathematics. I understand how that works in physics through coarse graining and so on. I understand less well how that works in mathematics. And that's what I think this univalence axiom, these extensionality principles and so on are doing in mathematics, is implementing the we are computationally bounded. And I think the analog of that, I'm claiming my glib version of this is, in mathematics, all we keep are the theorems, we throw away the proofs.
Yeah.
And that somehow it's related to that. But, but this is the key point. This might not be possible. In other words, it might be the case that there's no way to, the mathematics that arises or the physics that arises when we sample things only in a computationally bounded way could still have irreducibility in it.
Okay, so that's exactly what I was about to tweak of what you said or join to it, which is if you think of us as fundamentally just randomly going on hunch or instinct or whatever, and you just think of that as random, as effectively random search, right? Like we don't know any better when we start. Causal invariance is what guarantees that random search will find pockets of.
That's a good point. Yeah, that's a good point. Right. Causal invariance guarantees random search can't get lost.
Yeah, exactly. Like you'll eventually hit something good.
We can't get lost, e.g. doing random search. Well, that's interesting. So that means, in other words, we don't have to be that smart to succeed in getting something to work.
But we will, but again, this to go back to the gravitational lensing thing, if what we're doing is ultimately quite stupid, and this is not meant to be an insult against the practice of mathematics, but if what we're doing is quite random and mechanical, ultimately, then we will perceive like this undue influence of certain theorems, right? That seem to have this effect that they, I mean, maybe this analogy is a bit too glib, but like, yeah, they bend us into causally invariant areas of metamathematical space, right? And we will just come to observe these theorems as being useful and magical. But that's property of the curvature of, I don't know.
Yeah, right. But I mean, the question then is, for example, one proposed result is, which again has not been properly nailed down, non-constructiveness is on the border between constructive proofs and undecidability. That would be an example of a result, of a general result about kind of metamathematics. And, but again, it will be, the thing I'm still struggling with is what's the question, so to speak. Like in general relativity, the question is, what is the relationship between mass and motion? Right? So the question here is, what is the relationship between something like the accumulation of lemmas and proofs? I mean, because what's weird is that unlike, in physics, see, one of the things that's also quite strange, in physics, we at least imagine that we're just sort of putting down a configuration of masses, and then we see what happens. We're doing an experiment. But in mathematics, it's not quite the same way, I don't think. Or maybe it is. Maybe we're putting down certain axioms, but I don't think it is that way, because axioms are like the laws of physics. And there's something, I mean, it confuses me rather. We should probably wrap up. You're getting tired, and I have things I have to do before I go on to some other event that I'm going to. We're making progress. It's slow, but in trying to
I mean, the thing that, if I can summarize what I've been particularly inspired by, it's kind of nail what I don't know what coordinatization might be like in mathematical. That feels like a profitable thing to understand better.
Models, coordinate systems, those kinds of things. And we haven't really talked about, I mean, things like undecidability and so on, where we're dealing with infinite. I mean, that's just a grown-up version of computational irreducibility, although I don't fully understand how, irreducibility has the consequence it makes mathematics hard to do. Undecidability has the consequence that it makes mathematics incompletable, so to speak. That is, it is one thing to say, we're making this lemma, it stretches out, we're taking this long sequence in this multi-way system, or we're crushing it together. But to say that there isn't necessarily even, we could have an infinite length thing that the thing we're asking about may not be of any bounded length is a slightly different issue. All right, well, it's, we're slowly making progress. I'm now, I was all steaming ahead writing something about the physicalization of metamathematics, so to speak. But I'm now
chastened.
What's that? Yes, basically. I mean, it's one of these situations where I know I have a certain level of understanding, but I think that there is a much higher level of understanding that can be achieved. And it's not clear. It may be that because of my process of writing things, which forces me to have a certain level of understanding, that basically it's not reachable, so to speak. That, if I try and do if I try and skate by writing what I know so far, all that's going to happen is that I'm just going to get stuck because there'll be things that are unskateable, so to speak. I'm sure there's an analogy right here in what we've been doing. But the thing, I mean, again, yeah, I mean,
well, another takeaway is just that this is rich. Like, there's a rich pool of things going on.
Look, but I mean, in terms of mathematics, one of the claims would be that, okay, we know mathematics is boundless, but the question is doable mathematics boundless? Or is mathematics going to hit a wall where it stops being doable? And where most of the things in it, how uniformly doable is mathematics? That's a good meta-mathematical question. Because, for example, in studying cellular automata, you rapidly hit walls in many directions. I mean, listen, this whole thing has led me to another question, which is, I have long believed that studying things like cellular automata, you hit a wall. But could it be the case that there is a type of theory of those things, like the types of theories that we have of physics now, or of mathematics, that skate over the apparent irreducibility of those systems? In other words, it seemed like you're either deep down in the irreducibility or you've got nothing.
Well, you must have knowledge of, I mean, you must remember all of the things that you tried with in NKS with CAs, but the thing that comes to mind is something similar to what you do with like normalization, where I guess in the CA model, it would be, you're just going to have blocks of larger numbers of pixels.
And that doesn't work.
And then treat that as a meta CA of some kind. Does that not yield anything?
I don't know that it yields anything. I never managed to make it yield anything. I mean, that's you know, basically, you know, is there a way of deducing? I mean, is there a systematic way of extracting reducibility from these irreducible systems? And the claim is,
okay, no. Is the claim no? What's the claim?
The claim is that in physics, we managed to find a way to do it. That's the achievement of 20th century physics, basically, is to do that.
Yeah. Mining the reducibility out of the
and that we've got one way to do it. We may not have found the only way to do it. We found one way to do it based on our sensory data and our whatever. I mean, the alien physics could be utterly different.
Yeah, but I mean, that's I was going to suggest that as a potential irony of a 25th century computer scientist, whatever, looking back on your treatise, they might say, well, if only Stephen had known 24th century computer science, like would have cracked a lot of the CAs. And it just required new structures that we haven't invented yet that are very alien.
Right, exactly.
So you might have hit the forest might have changed to a different kind of vegetation that we're just not equipped to do anything about.
Well, I know, but that's my claim about physics, that the physics we have, and that there can be completely, disjoint theories of physics that simply look at completely different things. I mean, it's similar to my claim, molecules of gas in a room, we describe them in terms of pressure and temperature, but there's obviously a huge amount of other information, which we just say, oh, that's kind of random. And yes, you're right. I mean, in some respects, some areas of science are a story of noticing things that were never noticed before. I mean, if you look at, I don't know, a random, animal, and you say, well, it has this structure, but you're not looking down at the molecular level at, the individual, once you look at the molecular level, you see a whole different form of description that wasn't possible before. And I think you're quite right, that there's forms of description that we just don't know yet.
So there could be a relativized version of computational irreducibility that just says there's a complicated graph of like what kinds of computational analysis or system can break other kinds. And
yes,
there's just a whole logic of that we don't know yet, but that might have intricate structure that could be quite fascinating, etc.
Right. No, I agree. I mean, I think that we know a certain slice. I mean, look, if we really want to get crazy about it, it's kind of the story of the hopelessness of extraterrestrial intelligence, so to speak. I mean, that is that the slice of things that we know is, I mean, we are completely folded back on ourselves, of the things that we consider significant, of the things that we recognize, et cetera, et cetera, et cetera. It's a story that there's, which we're seeing again in the case of this mathematics. Some questions on our live stream. Let's see. Would an irreducible lemma be analogous to a point of maximum entropy, so you can't reduce it without losing information? Something like that is true, but entropy is a very complicated concept in the case of, I mean, we don't have a notion of, in metamathematics, we don't have a notion of ensembles in metamathematics. There's a point from Jose here that David Deutsch's constructor theory is physics without probabilities. Since we got to understand constructor theory. I sent David a mail actually recently. I don't think I got a response yet. Basically, more or less saying we need to understand constructor theory.
What I like about constructor theory is that, and this is more, I think it's more general. He's very skeptical that probabilities are a real fundamental thing, at least non-determinism.
Well, right, and we have that situation as well. I mean, obviously, in our multi-way systems, there are no probabilities. It's just it's a thing, and I think that I mean, the other thing that's interesting about this approach to metamathematics is this whole sort of mathematics invented versus discovered. This is kind of, operationalizing that issue. There is a multi-way graph. It goes on forever. It is what it is. We are exploring a piece of it. And that piece is a piece that we are discovering. But, I mean, but yet the choice of what piece we explore, anyway, I'm still, I think this point.
It's a very circular exercise, which is one of the things that makes it confusing, because it's mathematics is so, in a sense, narcissistic, right, in its focus, pure mathematics.
Yes.
It makes it very difficult to kind of
but I
model
think
it
the
as
point
an
is
enterprise.
Look, I mean, the fact is that insofar as our physics project is reducing essentially physics to mathematics, it's just saying this whole physical universe of ours, it's just certain rules and you apply them and it does the universe. We have an experience of physics insofar as our universe is just this formal system. We have ways of describing how that formal system works that correspond to our physical experiences, right? So what I'm asking is, what are the similar kinds of descriptions that we can give of metamathematics, which is structurally, because metamathematics in this idea of physics, of computationalism of everything, the metamathematics is the same kind of thing as the physical universe. So the question is, how do we describe our experiences in metamathematics in the same kind of intuitive way, in a sense, that we're describing our experiences in physics? And how do we, right? And how do we say, that, how do we, for example, set up the analog of reference frames, all those kinds of things? I think I need to rush off. It's really late for you, I know. And we've been getting all kinds of interesting comments from our live stream, which I appreciate. And we should probably wrap up for today and continue another time. And I will put this notebook in our main repository so that will show up for you and everybody else.
Thanks.
Certainly by tomorrow. That was fun. And I know, Tally, I know we have on the docket to talk about biological evolution as well. And I look forward to doing that in the next couple of days.
Yeah, that'd be awesome. Okay, cool.
All right.
Okay.
So,
well,
see you later.
Bye to all the viewers. Cheers.
Yeah.